What lies beyond our skies? How does the universe operate in the vast, silent void of space? What forces shape the stars, planets, and galaxies that captivate us every night? In this video, we'll dive into the fascinating physics of space, from the fiery power of our sun to the icy mysteries of distant planets. Can we truly understand the universe's mechanics, or are we just beginning to scratch the surface? Join us on this journey through space and time to explore the wonders that define our cosmic neighborhood and our place within it. In the early days of our solar system, 4 small rocky planets formed in the region closest to the Sun. Here, the young star's intense radiation was strong enough to blow away light gases and destroy all ice. However, farther from the Sun, a different story unfolded. Hydrogen, helium, and ices like water and methane were abundant. In this colder, distant region, 4 colossal planets were born: Jupiter, Saturn, Uranus, and Neptune. These gas giants dominated the young solar system, their immense gravity pulling in nearly all the available gas and debris around them. Human curiosity has always reached for the stars, and these massive outer worlds held a special allure. While humanity had explored the rocky inner planets, Mercury, Venus, and Mars, the gas giants presented a new frontier that demanded exploration. They were distant, mysterious, and filled with secrets waiting to be uncovered. To reach these outer giants, spacecraft first had to navigate a treacherous zone, the asteroid belt. This vast region, located between Mars and Jupiter, is a protoplanetary graveyard filled with rocky remnants left over from the solar system's formation. Stretching 160 million kilometers beyond Earth's orbit, it presented an intimidating obstacle. When NASA's Pioneer 10 became the first spacecraft to cross the asteroid belt, many wondered whether it could survive. In popular imagination, the asteroid belt is often depicted as a chaotic region, with rocks colliding dramatically. The reality, however, is far less dramatic. The belt is vast, and its debris is widely spread out. Scientists calculated that Pioneer 10 faced only a 1 in 1,000 chance of a serious collision. 7 months after entering the belt, Pioneer 10 emerged unscathed, marking a triumphant milestone in humanity's journey to the outer planets. By the end of its mission, the spacecraft completed a historic flyby of Jupiter, using the planet's immense gravity to slingshot itself toward the edge of the solar system. For decades, Pioneer 10 held the title of humanity's most distant spacecraft, a record it kept until 1998. In the 1960s, engineers at NASA's Jet Propulsion Laboratory recognized a once-in-a-lifetime opportunity. The outer planets were aligning in such a way that a single spacecraft could use their gravity to hop from one planet to the next, dramatically reducing the fuel required. This rare alignment, occurring only once every 176 years, inspired the idea of a grand tour of the outer solar system. Missing this opportunity would mean waiting nearly 2 centuries for another chance. NASA responded with the Voyager program, a groundbreaking mission designed to explore these distant worlds. 2 identical spacecraft, Voyager 1 and Voyager 2, were launched to take advantage of the alignment. The goal wasn't just to study the planets in detail, but also to send probes capable of lasting decades in the harsh environment of space. By today's standards, the Voyagers were relatively simple machines. Their cameras were comparable to those found in television studios of the 1970s, and their data was recorded on 8-track tape. Yet, despite their simplicity, they were marvels of engineering, equipped to deliver groundbreaking discoveries. Each Voyager carried a cultural message from humanity: the Golden Record. Spearheaded by Carl Sagan, This record contained 115 images, 90 minutes of music, and greetings in 55 languages. It was a time capsule, a message of peace and curiosity intended for any extraterrestrial life that might one day encounter the probes. More importantly, it symbolized humanity's collective spirit of exploration and our desire to connect with the universe. Voyager 2 launched first, followed 2 weeks later by Voyager 1. Within 2 years, both spacecraft reached their first destination, Jupiter, the largest planet in our solar system. With a mass 2.5 times that of all the other planets combined, Jupiter is a true giant. It formed during the early days of the solar system, growing by devouring smaller bodies like asteroids and comets. Eventually, it cooled enough to accumulate a massive envelope of gas surrounding a dense core. Jupiter is more than just a planet. It's a dominating presence in the solar system, second only to the Sun in influence. Pioneer 10 had already provided humanity with the first close-up images of Jupiter, but the Voyagers revealed the planet in even greater detail. One of their key targets was Jupiter's Great Red Spot, a massive storm that has raged for centuries. This swirling cyclone is similar to hurricanes on Earth, but on a far grander scale. When first observed nearly 400 years ago, the storm was large enough to fit 3 Earths across. By the time the Voyagers arrived, it had shrunk to the size of 2 Earths, a reminder of Jupiter's dynamic and ever-changing nature. The Voyagers also made an unexpected discovery. Jupiter had faint rings. Unlike Saturn's bright and iconic rings, these were subtle and almost invisible, composed of dust likely shed by the planet's moons. This revelation hinted at a surprising truth. Every gas giant in our solar system has rings, though many are difficult to detect. Jupiter's moons were another major focus for the Voyagers. Galileo's discovery of the planet's 4 largest moons, Io, Europa, Ganymede, and Callisto, had revolutionized our understanding of the cosmos centuries earlier. The Voyagers continued this legacy, revealing these moons to be diverse worlds in their own right. Io, the most volcanically active body in the solar system, stunned scientists with its fiery surface. Europa, with its smooth, icy crust, raised tantalizing questions about the possibility of a subsurface ocean and, perhaps, life. Ganymede, the largest moon in the solar system, was revealed to have its own magnetic field, while Callisto's ancient cratered surface spoke of a long and tumultuous history. The Voyagers' journey didn't end with Jupiter. They continued on to Saturn, Uranus, and Neptune, uncovering the secrets of each planet and their moons. These spacecraft, designed for a mission of just a few years, have far exceeded expectations, continuing to transmit data from the edges of interstellar space. The Voyagers represent humanity's insatiable curiosity and determination to explore. They remind us of the vastness of our universe and the small but significant role we play within it. Today, they continue their silent journey, carrying humanity's message to the stars, a testament to our desire to understand the cosmos. In 1610, Galileo Galilei turned his telescope to the night sky and made discoveries that would forever change our understanding of the universe. By observing Jupiter's 4 largest moons, Io, Europa, Ganymede, and Callisto, he provided evidence that not everything revolved around Earth. This revelation challenged the geocentric model, paving the way for our modern understanding of a heliocentric solar system. Among these moons, Io stands out as a volcanic inferno. With over 400 active volcanoes, it is the most volcanically active body in the solar system. Its surface is a chaotic mix of lava flows and sulfur, shaped by the moon's elliptical orbit around Jupiter. Normally, a moon's core would cool over time, But Io's proximity to Jupiter subjects it to immense tidal forces. These gravitational tugs stretch and compress Io, causing its surface to bulge by as much as 100 meters. The resulting friction generates enough heat to keep its interior molten, fueling its volcanic activity and creating a hellish landscape. While Io's fiery surface captures attention, it is Europa that holds the greatest intrigue. Beneath its thick, icy crust lies a vast ocean of liquid water, possibly containing more water than all of Earth's oceans combined. Evidence suggests that this ocean circulates, with currents breaking through the ice and reshaping the surface. This movement creates an environment with three essential ingredients for life: liquid water, energy, and organic compounds. On Earth, these same conditions gave rise to life within 1 billion years. Scientists believe Europa could be one of the best places to search for extraterrestrial life in our solar system. The quest to understand Jupiter and its moons took a giant leap forward with the Galileo spacecraft, launched in 1989 aboard the shuttle Atlantis. Its journey to Jupiter spanned 6 years, but along the way, Galileo witnessed one of the most dramatic events in solar system history. In 1994, the spacecraft observed the comet Shoemaker-Levy 9 as it was torn apart by Jupiter's gravity. When fragments of the comet collided with Jupiter's atmosphere, they released energy far greater than all of Earth's nuclear weapons combined. The impacts left massive scars, some thousands of kilometers wide, visible on Jupiter's surface for months. This event was a stark reminder of Jupiter's role as the solar system's gravitational guardian. Its immense pull has likely deflected countless comets and asteroids that might otherwise have struck Earth, shaping the conditions that allowed life to flourish here. In 1995, Galileo reached Jupiter, accompanied by a small atmospheric probe designed for a brief but groundbreaking mission. The probe plunged into Jupiter's thick clouds, descending 180 kilometers into the planet's atmosphere before being vaporized. During its descent, it measured temperatures, pressures, and lightning activity, confirming theories about Jupiter's turbulent atmosphere. Meanwhile, the main spacecraft began a series of 35 orbits around Jupiter, studying its moons and magnetic field in unprecedented detail. To protect Europa and other moons from potential contamination, Galileo was intentionally destroyed in 2003 by steering it into Jupiter's atmosphere. This ensured that no Earth microbes accidentally carried by the spacecraft would interfere with the pristine environments of these distant worlds. For more than a decade after Galileo's mission, Jupiter remained under distant observation. In 2016, NASA's Juno spacecraft arrived to continue the investigation. Unlike its predecessors, Juno was designed to reveal what lies beneath Jupiter's thick clouds and explore the planet's mysterious interior. Juno orbits Jupiter in a highly elliptical path, skimming as close as 8,000 kilometers to the planet's surface, akin to flying a few centimeters above a basketball. These close passes allowed Juno to map Jupiter's internal structure and study its powerful magnetic field, which is 20,000 times stronger than Earth's. Beneath the planet's clouds, hydrogen is compressed into a metallic form, creating currents that generate the magnetic field. Juno's findings have helped scientists better understand how gas giants like Jupiter form. By revealing details about its core, atmosphere, and gravity, Juno has provided clues about the early days of our solar system and the processes that shaped its largest planet. As the Voyagers completed their studies of Jupiter in the 1980s, they turned their attention to Saturn, the second largest planet in the solar system. Named after the Roman god of agriculture, Saturn has been a fixture in human observation for centuries. Early astronomers, including Galileo, marveled at its unusual appearance. Using his modest telescope in 1610, Galileo described Saturn as having ears, unable to clearly discern its rings. In 1659, Dutch astronomer Christian Huygens, with a more advanced telescope, correctly identified these features as a vast ring system encircling the planet. The Voyager's approach to Saturn revealed a wealth of new information. Its rings, stretching 200,000 kilometers across but only about 10 meters thick, consist of countless particles of ice and rock. These range in size from tiny dust grains to massive boulders, all orbiting Saturn at incredible speeds of up to 880,000 kilometers per hour. Beyond their breathtaking beauty, Saturn's rings hold clues about the planet's history. Some theories suggest the rings formed from the remnants of a shattered moon or comet, while others propose they are ancient structures as old as the solar system itself. The Voyagers also discovered new, fainter rings and provided detailed images of Saturn's moons, each a world of its own. Saturn is home to an impressive family of moons, with over 80 identified to date. Among them, Titan stands out as the largest and most intriguing. Titan is the only moon in the solar system with a thick atmosphere, rich in nitrogen and hydrocarbons. Its surface features lakes and rivers of liquid methane, raising the possibility of exotic forms of life. Another moon, Enceladus, captivated scientists with its geysers of water vapor erupting from cracks in its icy surface. These plumes suggest the presence of a subsurface ocean, similar to Europa's, making Enceladus another prime candidate in the search for life beyond Earth. The Voyager missions transformed our understanding of the outer solar system. They revealed the complex interplay of forces shaping the gas giants and their moons, uncovering phenomena that continue to inspire exploration. As they ventured beyond Saturn, the Voyagers carried humanity's curiosity to Uranus, Neptune, and beyond, transmitting data from the farthest reaches of the solar system. Today, missions like Cassini, Juno, and future projects aim to build on this legacy, delving deeper into the mysteries of our celestial neighbors. These spacecraft not only expand our scientific knowledge, but also remind us of the boundless potential of human ingenuity and the enduring desire to explore. The origin of Saturn's rings has long puzzled scientists. Were they ancient structures formed alongside the planet, or did they appear later through a cosmic accident? Recent evidence points to the latter, a relatively recent event, cosmically speaking. It's believed that a once intact ice moon strayed too close to Saturn. The planet's immense gravitational forces tore it apart, scattering the debris into the stunning rings we see today. These rings are not static. They are dynamic and ever-changing. The Cassini mission provided unprecedented insight, revealing that the rings rain water and icy particles onto Saturn at a rate of 40 tons per second. This phenomenon transforms the rings into a fleeting feature of Saturn's history, suggesting they may one day disappear entirely. The story of the Cassini-Huygens mission begins with Titan, Saturn's largest moon. Discovered in 1655 by Christian Huygens, Titan remained shrouded in mystery due to its thick, hazy atmosphere. Early glimpses from Voyager, one hinted at an alien world unlike anything in our solar system. But much of Titan's surface was obscured. In 1997, NASA, ESA, and the Italian Space Agency launched the Cassini-Huygens mission, combining international expertise to explore Saturn and its moons. This collaboration was born from the tantalizing discoveries made by the Voyager missions, which revealed Saturn to be more complex and captivating than previously imagined. The mission consisted of two spacecraft, Cassini, a NASA-led probe designed to orbit Saturn, and Huygens, a European-designed lander created to explore Titan. This joint effort achieved groundbreaking discoveries that exceeded even the most ambitious expectations. After a 7-year voyage, Cassini arrived at Saturn in 2004, becoming the first spacecraft to orbit the planet. The mission faced immediate challenges as Cassini navigated the planet's iconic rings. Each pass through the debris-filled region required precise calculations to avoid collisions. Scientists and engineers held their breath with every crossing, knowing even a small particle could damage the spacecraft. Cassini's daring maneuvers paid off, providing detailed images of Saturn's rings. These snapshots revealed intricate structures and varying compositions, including fine icy particles and chunks of rock. The spacecraft also discovered new phenomena, such as the Great White Spot, a massive storm, and the hexagonal hurricane at Saturn's North Pole, 50 times larger than any hurricane on Earth. In December 2004, Cassini released the Huygens probe, which began its descent to Titan on Christmas Day. After a 22-day journey, Huygens entered Titan's atmosphere, becoming the first spacecraft to land on a moon in the outer solar system. The probe's descent lasted 2.5 hours, during which it transmitted invaluable data about Titan's atmosphere and surface. It revealed a landscape eerily reminiscent of early Earth: ice mountains, vast sand dunes, and networks of river-like channels. However, these rivers didn't flow with water. Instead, liquid methane and ethane, organic compounds found in Titan's atmosphere, carved their way across the moon's icy surface, pooling into large lakes. Titan's conditions evoke a primordial version of Earth, offering a glimpse into the planet's past. The presence of complex organic molecules raises tantalizing questions. Could life exist on Titan? If so, would we even recognize it, given how different it might be from life as we know it? While Titan initially captured most of the mission's attention, another of Saturn's moons soon emerged as an equally compelling target: Enceladus. This small, icy moon surprised scientists with its dramatic water geysers erupting from cracks in its surface. These plumes, visible from space, are evidence of a subsurface ocean of liquid water beneath Enceladus's frozen crust. Cassini flew through these geysers, sampling the water vapor and detecting complex organic molecules. The discovery of salts and warmth within the ocean suggested the presence of hydrothermal vents on the ocean floor. On Earth, similar vents support thriving ecosystems, leading scientists to consider Enceladus one of the most promising locations for finding extraterrestrial life. Unlike Titan, landing on Enceladus isn't necessary to study its ocean. The geysers eject material into space, allowing future missions to sample the moon's secrets without touching its surface. Enceladus has become a focal point for astrobiology, representing one of the best chances to discover life beyond Earth. After nearly 20 years in space, Cassini's fuel supply began to dwindle. Instead of abandoning the spacecraft, NASA devised a bold finale. In 2017, Cassini embarked on the Grand Finale, a series of daring orbits between Saturn and its innermost ring. For the first time, Cassini ventured into the gap between the planet and its rings, sending back valuable data about the region's composition. These final maneuvers culminated in a dramatic end. On September 15, 2017, Cassini plunged into Saturn's atmosphere, burning up like a meteor. This intentional act ensured that no Earth microbes aboard the spacecraft could contaminate Saturn's moons, preserving them for future exploration. Cassini's journey transformed our understanding of Saturn and its moons. It revealed a dynamic system of rings, complex weather patterns, and worlds with the potential for life. The mission's discoveries continue to inspire scientists and fuel plans for future exploration of the outer solar system. Cassini-Huygens left behind a legacy of discovery, but it also raised new questions. What lies beneath Titan's methane lakes? Could drones dive into Enceladus's ocean to search for life? These questions drive the next generation of space exploration. Proposed missions, such as NASA's Dragonfly drone for Titan and a possible Enceladus orbiter, aim to build on Cassini's success. These advanced spacecraft will carry cutting-edge instruments to answer humanity's most profound questions. Are we alone in the universe? The Cassini mission exemplifies the spirit of exploration and international cooperation. It reminds us that, even 1.4 billion kilometers from Earth, we can uncover the secrets of distant worlds. As we look to the future, Saturn and its moons remain a beacon of possibility, inviting us to continue our journey into the unknown. In 2019, astronomers finally solved one of Saturn's long-standing mysteries, the age of its rings. Far from being as ancient as the planet itself, the rings are surprisingly young, formed just 10 to 100 million years ago, a mere blink in the 4.5 billion-year history of the solar system. Evidence suggests they originated from an icy moon that strayed too close to Saturn, torn apart by the planet's gravity, and transformed into the iconic rings we see today. The Cassini mission, which had provided so much insight into Saturn and its moons, ended in 2017 with a dramatic finale. With its fuel running low, Cassini was deliberately plunged into Saturn's atmosphere to prevent contamination of the planet's moons. Even in its final moments, the spacecraft transmitted critical data about the upper atmosphere. Within 45 seconds of losing signal, Cassini burned up, marking the end of one of humanity's most ambitious space missions. While Cassini was designed to orbit Saturn, the Voyager probes were tasked with exploring much farther. 4 decades earlier, Voyager 1 left Saturn after a brief encounter with Titan, embarking on a lonely journey toward interstellar space. Its twin, Voyager 2, took a different path, visiting the remaining unexplored planets, Uranus and Neptune. Uranus, the 7th planet from the Sun, was discovered in 1781 by Sir William Herschel. Initially mistaken for a comet, Uranus was the first planet to be discovered with the aid of a telescope, breaking the long-held assumption that all planets visible to the naked eye were already known. In January 1986, Voyager 2 flew within 82,000 kilometers of Uranus's cloud tops, unveiling a planet unlike any other. Uranus is tipped over on its side, with an axial tilt of 98 degrees, likely caused by a massive collision with an Earth-sized object billions of years ago. This unusual orientation creates extreme seasonal variations, with one pole facing the Sun for half of its 84-year orbit, while the other remains in darkness. Voyager 2 revealed that Uranus's atmosphere is the coldest in the solar system, with temperatures plunging to a frigid -224 degrees Celsius. This icy world glows a pale blue-green, a result of methane in its atmosphere, absorbing red light and reflecting blue. Voyager also discovered 11 faint rings around Uranus, some of which had been detected earlier by ground-based observatories, but others were revealed only by the probe's close observations. The spacecraft also provided a closer look at Uranus's moons, particularly Miranda, one of the most bizarre objects in the solar system. Miranda's surface is a patchwork of deep canyons, cliffs, and smooth plains, as though the moon had been shattered and poorly reassembled. Voyager 2's images captured breathtaking features, including cliffs over 20 kilometers high. Due to Miranda's low gravity, an object falling from these cliffs would take nearly 20 minutes to reach the surface, making it a hiker's dream, if not for the extreme cold. 3 years after its encounter with Uranus, Voyager 2 arrived at Neptune, the outermost planet of the solar system. Discovered in 1846 through mathematical predictions rather than direct observation, Neptune had been a mystery for centuries. To communicate with Voyager 2 at such an immense distance, NASA expanded its deep space network in the late 1980s. This global system of radio antennas, spread across California, Spain, and Australia, allowed engineers to send commands to Voyager and capture its faint signals, like whispers across the void. In August 1989, Voyager 2 flew within 4,950 kilometers of Neptune's cloud tops, revealing a vibrant blue planet dominated by fierce winds, the fastest in the solar system, reaching speeds of over 2,000 kilometers per hour. The probe captured images of the Great Dark Spot, a massive storm system similar to Jupiter's Great Red Spot, but temporary, as it disappeared in later observations. Neptune's largest moon, Triton, proved equally fascinating. Voyager 2 discovered that Triton orbits Neptune in the opposite direction of the planet's rotation, a retrograde orbit suggesting the moon was likely a captured object from the Kuiper Belt. Triton's surface, covered in nitrogen ice, features active geysers spewing dark material into its thin atmosphere. These discoveries hinted at a dynamic world, despite temperatures hovering near absolute zero. Voyager 2's flyby of Neptune marked the end of humanity's first and only exploration of the ice giants. The brief encounters revealed that Uranus and Neptune are not merely scaled-down versions of Jupiter and Saturn, but unique worlds with distinct characteristics. Despite the decades that have passed, no spacecraft has returned to the ice giants, leaving them largely unexplored. Beyond Neptune lies the Kuiper Belt, a vast region of icy bodies that includes dwarf planets like Pluto. Stretching billions of kilometers from the Sun, the Kuiper Belt is a frozen remnant of the early solar system, containing objects that never coalesced into larger planets. Although the Kuiper Belt was theorized for decades, it wasn't confirmed until 1992, when astronomers detected its first object. Voyager 2 passed through this mysterious region on its way out of the solar system, but its instruments were not designed to study these distant worlds. Pluto, once considered the 9th planet, resides within this icy frontier. Demoted to a dwarf planet in 2006, Pluto remains one of the most intriguing bodies in the Kuiper Belt. In 2015, NASA's New Horizons mission provided humanity's first close-up view of Pluto, revealing a surprisingly complex world with mountains of water ice, vast nitrogen plains, and evidence of geological activity. The Voyager probes, launched in 1977, were designed to last only 5 years, yet they continue to operate more than 4 decades later. In 2012, Voyager 1 became the first human-made object to enter interstellar space, crossing the heliopause, the boundary where the Sun's influence ends and the interstellar medium begins. Voyager 2 followed in 2018, providing humanity with its second interstellar messenger. Both probes carry the Golden Record, a time capsule containing images, sounds, and messages from Earth. Designed by Carl Sagan and his team, the record serves as a greeting to any extraterrestrial civilization that might one day encounter the Voyagers. It's a testament to humanity's curiosity and desire to connect with the universe. The ice giants and the Kuiper Belt remain ripe for exploration. Proposed missions to Uranus and Neptune could unlock secrets about their origins, atmospheres, and moons, shedding light on the formation of our solar system. Meanwhile, the Kuiper Belt holds clues about the building blocks of planets and the conditions that shaped the early solar system. Beyond these frontiers, astronomers look to the stars, where exoplanets, planets orbiting other stars, offer a new frontier for discovery. Observatories like the James Webb Space Telescope promise to reveal details about these distant worlds, bringing us closer to answering one of humanity's greatest questions. Are we alone in the universe? The journeys of the Voyager probes, Cassini, and New Horizons are reminders of what we can achieve through curiosity, ingenuity, and perseverance. As we continue to push the boundaries of exploration, the lessons of the past guide us toward an ever-expanding understanding of the cosmos. In 1930, a young astronomer named Clyde Tombaugh discovered Pluto, a celestial body that captivated imaginations for decades. Classified as the 9th planet for much of the 20th century, Pluto was redefined as a dwarf planet in 2006. This change followed the discovery of similarly sized objects in the Kuiper Belt, a region of icy bodies beyond Neptune. While its planetary status shifted, humanity's fascination with Pluto remained undiminished. NASA's New Horizons mission, launched the same year, sought to explore this distant world and expand the legacy of the Voyager probes. New Horizons embarked from Cape Canaveral on January 19, 2006, carrying with it humanity's hopes to uncover Pluto's mysteries. Despite its relatively small size, Pluto had long eluded detailed study due to its immense distance, nearly 5 billion kilometers from Earth. Communication with the spacecraft posed a significant challenge. Radio signals took over 4 hours to travel each way, and data transmission speeds were painfully slow, just 1 kilobit per second, far slower than 1990s dial-up modems. Scientists waited eagerly for each image and data set, downloading updates over 15 months as New Horizons sent its treasure trove of information back to Earth. When New Horizons reached Pluto in 2015, it revealed a world far more dynamic than anyone had anticipated. Pluto's surface was adorned with nitrogen ice glaciers that flowed like rivers, carving paths through valleys and beneath mountains of water ice towering 3 kilometers high. These mountains, dusted with nitrogen snow, created a breathtakingly alien landscape. One of the most astonishing features was a heart-shaped region, later named Tombaugh Regio, which hinted at a young surface, possibly formed within the last million years. This was a stark contrast to the heavily cratered terrain scientists had expected. As New Horizons departed, it captured Pluto's blue skies, created by nitrogen gas scattering sunlight, an echo of Earth's own atmospheric phenomenon. This image, set against the black void of space, was a poignant reminder of the diversity and beauty of our solar system's outer reaches. The exploration of the Kuiper Belt has revealed not only new worlds, but also raised questions about the gravitational forces shaping their orbits. Some of these objects follow unusual paths, suggesting the presence of a massive unseen body, dubbed Planet 9. Mathematical models and computer simulations point to a super-Earth-sized planet, 5 to 10 times the mass of our planet, orbiting 20 times farther from the Sun than Neptune. Such a distant planet would be extremely faint, reflecting very little sunlight, and likely obscured by the dense star fields of the Milky Way. Detecting Planet 9 is akin to searching for a needle in a haystack, where the needle blends in with the hay. Scientists hypothesize that this elusive planet may take 10,000 to 20,000 years to complete a single orbit around the Sun. Its discovery would profoundly alter our understanding of the solar system's structure and history, but until then, Planet 9 remains an intriguing mystery. While New Horizons ventured into the Kuiper Belt, the Voyager probes continued their silent journey into interstellar space. In 1990, Voyager 1 turned its camera back toward the inner solar system, capturing a family portrait of the planets. Among the images was the famous pale blue dot, a tiny speck of Earth suspended in a beam of sunlight. This photograph, taken from a distance of 6 billion kilometers, served as a humbling reminder of our planet's fragility and the vastness of the cosmos. Voyager 1 crossed into interstellar space in 2012, followed by Voyager 2 in 2018. They became humanity's first ambassadors to the stars, carrying golden records inscribed with images, sounds, and greetings in multiple languages. These records were designed to represent the diversity of life and culture on Earth, a message to any extraterrestrial intelligence that might encounter the probes. Despite being launched in 1977, the Voyagers continue to send data back to Earth, though their power supplies are expected to run out by the mid-2030. Their discoveries reshaped our understanding of the outer solar system, revealing the complexity of planets like Jupiter, Saturn, Uranus, and Neptune. The milestones achieved by the Voyagers, Cassini, and New Horizons have inspired new generations of scientists and engineers. Missions to the outer solar system have shown that even the most distant and inhospitable worlds can hold surprises. Saturn's moon Enceladus, with its subsurface ocean and geysers, has become a prime candidate for the search for extraterrestrial life. Similarly, Titan's methane lakes and thick atmosphere hint at chemistry that could support exotic forms of life. Proposals for future missions to these moons, as well as to Uranus and Neptune, are already in development. Exploring the ice giants would provide critical insights into planetary formation and the diversity of worlds in our galaxy. The exploration of space began with competition. As World War II ended, the United States and the Soviet Union scrambled to claim Germany's scientific knowledge and technology. The development of the V-2 rocket, the world's first long-range ballistic missile, laid the foundation for space exploration. Capable of crossing the threshold of space, the V-2 represented a leap in human engineering. The U.S. secretly evacuated thousands of German scientists and engineers through Operation Paperclip, including Wernher von Braun, who would later design the Saturn V rocket that carried Apollo astronauts to the moon. This influx of expertise fueled America's space program and its rivalry with the Soviet Union. The Cold War saw both nations stockpiling weapons and competing to achieve technological supremacy. The Soviet Union launched Sputnik in 1957, the first artificial satellite, igniting the space race. In response, the U.S. founded NASA and intensified its efforts, culminating in the Apollo program and the historic moon landing in 1969. Despite its origins in conflict, space exploration has evolved into a symbol of international collaboration. Missions like Cassini-Huygens and the International Space Station demonstrate what humanity can achieve when nations work together. The search for knowledge transcends borders, inspiring cooperation in the face of challenges that are too great for any one nation to tackle alone. As we stand on the shoulders of past explorers, the next chapter of space exploration beckons. Advances in technology, from artificial intelligence to reusable rockets, are opening new possibilities. The Artemis program aims to return humans to the moon and establish a sustainable presence there, serving as a stepping stone to Mars. Beyond our solar system, telescopes like the James Webb Space Telescope will peer into distant star systems, searching for planets that could harbor life. The discoveries of super-Earths and exoplanets have expanded our understanding of the cosmos, suggesting that Earth-like worlds may be common. The legacy of missions like Voyager and New Horizons reminds us that exploration is not just about discovery. It's about perspective. As we venture further into the cosmos, we gain a deeper appreciation for the interconnectedness of all life and the importance of preserving our pale blue dot. By the late 1950s, the space race was intensifying, with the United States and the Soviet Union vying to achieve the next milestone, sending a human into space. The Soviets had taken the lead with Sputnik, followed by America's quick response with Explorer 1. Now, both nations faced a new challenge, proving that humans could survive the harsh conditions of space and return safely to Earth. The first hurdle was understanding space itself. Beyond Earth's protective atmosphere lay an environment unlike anything experienced on our planet. The vacuum of space posed questions about how the human body would react. Would blood boil in the absence of pressure? Could muscles function in microgravity? How would extreme temperatures affect survival? There were no definitive answers, only theories and a sense of urgency to find out. The Soviet Union accelerated its efforts, drawing on their pool of military pilots to train as cosmonauts. Meanwhile, in 1958, the United States formed NASA, centralizing its efforts to compete in the space race. NASA's first human spaceflight program, Project Mercury, aimed to launch astronauts into orbit and return them safely. From a rigorous selection process, NASA chose 7 men to be the first Americans in space. These Mercury astronauts were announced on April 9, 1959, becoming instant national heroes. Nicknamed the Mercury 7, they were all military test pilots, chosen for their skill, composure under pressure, and physical endurance. They represented the best and brightest of their generation. A group of men willing to risk their lives to push the boundaries of human exploration. The Mercury program focused on sending a single astronaut into space aboard a small, one-person capsule. The mission objectives were straightforward but daunting. Test spacecraft systems, study the effects of weightlessness, and demonstrate that humans could function and survive in space. While NASA prepared for its first manned flight, the Soviet Union surged ahead. On April 12, 1961, Yuri Gagarin became the first human to journey into space aboard Vostok 1. His historic flight lasted just 108 minutes, during which he completed one orbit of Earth. Gagarin's success was a triumph for the Soviet space program and a blow to American pride. Gagarin's calm demeanor and infectious smile made him a global icon. He became a symbol of Soviet ingenuity and the human desire to explore. His achievement demonstrated that humans could survive in space, paving the way for longer and more ambitious missions. Determined to catch up, NASA launched Alan Shepard aboard Freedom 7 on May 5, 1961. Just weeks after Gagarin's flight. Shepard's suborbital mission, while shorter than Gagarin's, proved that Americans were capable of human spaceflight. He became the first American in space and an inspiration to millions. The United States reached another milestone on February 20, 1962, when John Glenn became the first American to orbit the Earth. Aboard Friendship 7, Glenn completed 3 orbits in just under 5 hours, demonstrating NASA's ability to match the Soviets' achievements. His flight cemented the Mercury program's success and restored America's confidence in the space race. The spacecraft of the early 1960s were engineering marvels, but also incredibly risky. Both the Soviet Vostok and the American Mercury capsules were cramped, with barely enough room for the astronauts to move. These early missions relied heavily on ground control, with limited autonomy for the pilots. The technology was rudimentary by today's standards. Computers were primitive, navigation was manual, and communications were limited. Astronauts faced enormous risks, from rocket malfunctions to life support failures. Yet every mission brought new knowledge, improving safety and refining the engineering for future flights. As both nations achieved success in orbital flight, they turned their attention to more complex missions. In 1965, cosmonaut Alexei Leonov performed the first spacewalk during the Voskhod 2 mission. Leonov spent 12 minutes outside his spacecraft, tethered by a safety line, as he floated in the vacuum of space. The achievement was not without peril. Leonov's suit inflated in the vacuum, making it difficult for him to re-enter the airlock. He had to release some of the suit's pressure manually, risking decompression sickness. Despite these challenges, Leonov's spacewalk marked a critical step toward the long-term human presence in space. Not to be outdone, NASA conducted its first spacewalk later that year. On June 3, 1965, astronaut Ed White exited the Gemini 4 spacecraft, becoming the first American to walk in space. Using a handheld propulsion device, White maneuvered outside the capsule, marveling at the view of Earth below. His spacewalk was a triumph, but it also highlighted the need for better tools and procedures for working in the vacuum of space. By the mid-1960s, both nations were looking beyond Earth's orbit. President John F. Kennedy's famous challenge to land a man on the moon and return him safely to Earth became the driving force behind NASA's Apollo program. The Soviets, meanwhile, pursued their own lunar ambitions, developing larger rockets and more advanced spacecraft. The race to the moon required innovations in every aspect of space exploration. Engineers developed new launch vehicles, like NASA's Saturn V, the most powerful rocket ever built. Scientists devised ways to navigate across hundreds of thousands of kilometers of space, rendezvous and dock with other spacecraft, and sustain human life for extended periods. The space race was more than a competition. It was a catalyst for technological and scientific progress. The demands of space exploration led to advances in materials, science, computer technology, and communications. These innovations filtered into everyday life, transforming industries and improving quality of life worldwide. The race also inspired a generation of scientists, engineers, and dreamers. It fostered international collaboration, as exemplified by later joint missions like Apollo-Soyuz, and set the stage for the development of the International Space Station. The achievements of the Mercury and Vostok programs laid the foundation for all subsequent human spaceflight. They demonstrated that humans could survive and thrive in space, opening the door to long-duration missions, planetary exploration, and the dream of interstellar travel. While the space race was born out of geopolitical rivalry, its legacy transcends national boundaries. The images of Earth from space, tiny, fragile, and alone in the vastness of the cosmos, remind us of our shared humanity and the need to care for our planet. As we look to the future, the spirit of exploration continues to inspire. New missions aim to return humans to the moon, send astronauts to Mars, and probe the outer reaches of our solar system. The story of space exploration is far from over, and the lessons of the past guide us toward an even more ambitious future. As the space race escalated, the United States and Soviet Union set their sights on achieving more complex missions. While the early one-person flights proved humans could survive space, the next step required multi-crew missions to perform more ambitious tasks. These missions demanded innovative engineering and carried greater risks. NASA's Gemini program, initiated in 1962, was designed to develop the skills and technology needed for the upcoming Apollo moon missions. Gemini's objectives included practicing orbital maneuvers, docking spacecraft, and performing spacewalks, all essential for future lunar exploration. Unlike the Mercury program, Gemini aimed to keep astronauts in space for up to 2 weeks, testing human endurance and the functionality of spacecraft systems over extended periods. Developing a 2-seat spacecraft wasn't as simple as scaling up Mercury's design. Engineers had to account for the increased mass, more powerful life support systems, and enhanced safety measures. Gemini's engineers innovated solutions to these challenges, creating a spacecraft that could sustain its crew in the harsh environment of space. Meanwhile, the Soviets raced to maintain their lead. Instead of developing a new spacecraft, they retrofitted their existing Vostok capsule to create Voskhod, capable of carrying multiple cosmonauts. However, these modifications came at a cost. To accommodate additional crew members, safety features were sacrificed. The Voskhod 1 mission launched in 1964, with 3 cosmonauts crammed into a capsule originally designed for 1. Without spacesuits or ejection seats, the crew had no protection against a catastrophic failure. The risks were enormous, but the mission succeeded, achieving a record altitude of 336 kilometers and showcasing the Soviets' willingness to push the limits. The next milestone in the space race was stepping outside the spacecraft, a feat achieved by the Soviets during the Voskhod 2 mission in 1965. Cosmonaut Alexei Leonov became the first human to conduct a spacewalk, exiting the spacecraft and floating freely in the vacuum of space. Leonov's spacewalk was both awe-inspiring and terrifying. Attached to the spacecraft by a tether, he spent 12 minutes outside, marveling at the view of Earth below. However, his spacesuit began to inflate in the vacuum, making it nearly impossible for him to re-enter the airlock. With quick thinking, Leonov released some of the pressure manually, risking decompression sickness. He barely managed to squeeze back inside the capsule, narrowly avoiding disaster. The achievement cemented the Soviet Union's dominance in the space race, but it also highlighted the dangers of space exploration. Leonov's experience underscored the need for improved suits, airlocks, and emergency procedures, lessons that would shape future missions. The Gemini program, while slower to start, allowed NASA to catch up and eventually surpass the Soviet Union in the mid-1960s. Gemini 4 marked America's first spacewalk, with astronaut Ed White floating outside the spacecraft for 23 minutes. White used a handheld propulsion device to maneuver, marveling at the beauty of Earth from space. His excitement was palpable as he declared the experience the greatest moment of my life. The Gemini missions pushed the boundaries of human spaceflight. Crews practiced docking maneuvers with uncrewed target vehicles, a critical skill for lunar missions. Gemini 6A and Gemini 7 performed the first rendezvous in space, flying within meters of each other in orbit. These missions demonstrated the precision and coordination required for complex operations in space. Gemini also tested human endurance. Gemini 7's astronauts spent 14 days in orbit, proving that humans could live and work in space for extended periods. These achievements laid the groundwork for the Apollo program and highlighted the United States' growing technical expertise. While Gemini advanced America's capabilities, the Soviet Union achieved another historic first in 1963 by sending Valentina Tereshkova into space aboard Vostok 6. Tereshkova became the first woman to travel to space, spending nearly 3 days in orbit. A former textile worker and amateur skydiver, Tereshkova's selection was both symbolic and practical. Her mission demonstrated that women could endure the rigors of spaceflight, challenging societal norms and expanding the potential pool of future astronauts. However, Tereshkova's flight was not without difficulties. She experienced space sickness and struggled to respond to ground control commands, raising concerns about the effects of prolonged space travel on performance. Despite these challenges, her mission was a landmark moment, inspiring generations of women to pursue careers in science, engineering, and space exploration. While Voskhod achieved significant milestones, it also exposed the dangers of prioritizing speed over safety. The lack of spacesuits and other protective measures on Voskhod missions demonstrated the Soviet program's willingness to accept extraordinary risks to stay ahead in the space race. The Voskhod program was short-lived, ending after just 2 missions. Its achievements were overshadowed by growing concerns about the sustainability and safety of the Soviet approach. By contrast, NASA's Gemini program emphasized methodical progress, testing and refining systems to ensure the success of future missions. By the mid-1960s, the space race was entering a new phase. The early focus on firsts, first satellite, first human, first spacewalk, shifted toward more ambitious goals. Both nations set their sights on the moon, a target that required unprecedented innovation and collaboration. The Soviet Union developed the N-1 rocket, a massive launch vehicle intended to rival NASA's Saturn V. However, repeated failures plagued the N-1 program, and the Soviets abandoned their lunar ambitions in the early 1970s. Meanwhile, NASA's Apollo program benefited from the lessons of Mercury and Gemini, culminating in the successful moon landing of Apollo 11 in 1969. The intense rivalry of the space race drove rapid advancements in science and technology, many of which continue to benefit humanity. Innovations in materials, science, computer technology, and telecommunications emerged from the demands of space exploration. These breakthroughs extended beyond space, transforming industries and improving everyday life. The competition also inspired a sense of global wonder and unity. The images of Earth from space, captured by astronauts and cosmonauts, highlighted the fragility of our planet and the shared responsibility to protect it. While the space race was fueled by geopolitical tensions, its legacy transcends national boundaries, reminding us of the power of human ingenuity and cooperation. The milestones achieved during the space race laid the foundation for modern space exploration. From the International Space Station to robotic missions exploring the outer planets, the spirit of discovery endures. As humanity looks to return to the Moon and venture to Mars, the lessons of Mercury, Gemini, and Voskhod serve as a guide. The space race was more than a competition. It was a testament to humanity's capacity for innovation, bravery, and exploration. It showed that the stars are not out of reach, and that, together, we can achieve the extraordinary. The space race between the United States and the Soviet Union wasn't just about technological innovation or lofty ideals of exploration. It was a battle for dominance. Both nations were willing to take extraordinary risks to achieve milestones that would demonstrate their superiority. The Soviet Union, in particular, pushed the boundaries with missions like Voskhod 2, which achieved humanity's first spacewalk, but at immense personal and technical peril. In March 1965, cosmonaut Alexei Leonov became the first human to step into the vacuum of space during the Voskhod 2 mission. Exiting the spacecraft through an inflatable airlock, Leonov was tethered to the Voskhod by a 5-meter cable. For a few breathtaking minutes, he floated above Earth, marveling at the fragile blue planet below. "I felt like a seagull with its wings outstretched," Leonov later wrote, describing the awe of seeing the Earth hanging in the vast darkness of space. However, Leonov's triumph quickly turned into a struggle for survival. His suit began to expand in the vacuum of space, making it nearly impossible for him to move or re-enter the airlock. With only minutes to spare before the spacecraft entered the Earth's shadow, Leonov made a desperate decision. He vented oxygen from his suit to reduce its volume, regaining enough mobility to squeeze back into the airlock. The challenges didn't end there. Explosive bolts used to detach the airlock caused the Voskhod to spin uncontrollably. The capsule overshot its landing site by 2,000 kilometers, forcing Leonov and his crewmate, Pavel Belyayev, to endure 2 frigid nights in a Siberian forest. Temperatures dropped below -25 degrees Celsius, and the cosmonauts had to fend off wolves while awaiting rescue. Despite these harrowing challenges, Leonov's spacewalk marked a pivotal achievement, demonstrating the feasibility of extravehicular activity, EVA. As both nations raced toward new milestones, the inherent risks of space exploration became painfully clear. In January 1967, tragedy struck NASA during a ground test for the Apollo program. A fire erupted inside the Apollo 1 capsule, killing astronauts Gus Grissom, Ed White, and Roger B. Chaffee. The incident revealed critical flaws in the spacecraft's design, from its highly flammable materials to its inward opening hatch, which prevented a swift escape. The Soviet Union suffered its own loss just months later. Vladimir Komarov, commander of the Soyuz 1 mission, became the first person to die during a spaceflight. The mission was plagued by technical failures, including faulty control systems and a parachute malfunction during re-entry. Unable to slow its descent, the Soyuz capsule crashed into the ground, killing Komarov instantly. His death highlighted the dangers of rushing untested systems into flight. These tragedies underscored the high stakes of the space race and prompted both nations to reevaluate safety protocols. NASA implemented major design overhauls for the Apollo program, while the Soviets suspended their lunar ambitions for 18 months. With the lunar race won by the United States in 1969, the Soviets shifted their focus to a new frontier: long-term habitation in space. In 1971, they launched Salyut 1, the world's first space station. Unlike previous missions, which lasted days or weeks, Salyut was designed for months-long stays, providing a platform to study the effects of extended weightlessness on the human body. The first crew to visit Salyut 1, Soyuz 10, was unable to dock due to a malfunction. The second crew, aboard Soyuz 11, successfully entered the station and spent 23 days conducting experiments. Tragically, their mission ended in disaster. During re-entry, a valve in the Soyuz capsule accidentally depressurized, killing all 3 cosmonauts. Despite the loss, the Soviets continued to refine their space stations, launching 7 Salyut stations over the next 2 decades. These missions pioneered techniques for living and working in space, from recycling air and water to conducting experiments in microgravity. In 1973, the United States launched its first space station, Skylab, constructed from spare parts of the Apollo program. Unlike Salyut, Skylab was equipped with modern amenities, including a galley, sleeping quarters, and even a zero-gravity shower. It served as a laboratory for studying the effects of microgravity on human physiology and conducting solar observations. Skylab's launch wasn't without problems. One of its solar panels was ripped off during ascent, and its sunshade, designed to protect the station from solar radiation, was damaged. The first crew sent to Skylab had to perform emergency repairs, including deploying a replacement sunshade and manually freeing the stuck solar panel. This spacewalk demonstrated the ingenuity and resilience of astronauts, who improvised solutions to save the mission. Over its operational life, Skylab hosted 3 crews, who collectively spent 171 days in orbit. The missions yielded valuable insights into how humans adapt to long-term spaceflight. Astronauts experienced fluid shifts, muscle atrophy, and bone density loss, requiring them to exercise for hours each day. Skylab also highlighted the psychological challenges of space travel. The third crew famously staged a mutiny, shutting off communications with mission control for an entire orbit to protest an overly demanding schedule. The incident forced NASA to rethink how it managed astronaut workloads, emphasizing the importance of balancing productivity with mental health. By the late 1970s, the competitive fervor of the space race began to give way to a spirit of cooperation. The Apollo-Soyuz test project in 1975 marked the first joint mission between the United States and the Soviet Union. Astronauts and cosmonauts docked their spacecraft in orbit, exchanged greetings, and conducted joint experiments. This historic handshake in space symbolized a new era of collaboration, laying the groundwork for future partnerships like the International Space Station, ISS. The space stations of the 1970s, both Salyut and Skylab, were stepping stones to the ISS, a multinational laboratory that has been continuously occupied since 2000. These early missions proved that humans could live and work in space for extended periods, paving the way for future exploration of the Moon, Mars, and beyond. The achievements of the space race, culminating in the development of long-term space habitats, demonstrated the resilience and ingenuity of humanity. While the rivalry between the United States and the Soviet Union spurred rapid advancements, it also revealed the universal challenges of space exploration. Today, the lessons learned from those early missions continue to shape our ambitions, reminding us of the risks and rewards of venturing beyond our home planet. As humanity prepares for its next chapter in space exploration, the legacy of Skylab, Salyut, and the Apollo-Soyuz missions serves as a foundation. Plans to establish permanent lunar bases, send humans to Mars, and develop new space habitats are rooted in the innovations of the past. The pioneers of the space race proved that with determination, creativity, and cooperation, the impossible can become reality. The space race began as a competition, but its greatest achievement was uniting humanity in the shared dream of reaching for the stars. In January 1967, the United States, Soviet Union, and United Kingdom signed the Outer Space Treaty, a landmark agreement that shaped the principles of space exploration. It sought to prevent the militarization of space, banning nuclear weapons in orbit, and emphasizing the peaceful use of celestial bodies for the benefit of all humanity. Amidst Cold War tensions, this treaty reflected a small but significant step toward cooperation in the final frontier. While geopolitical rivalries persisted, the idea of collaboration found its ultimate expression in the Apollo-Soyuz Test Project, ASTP, of 1975. For the first time, two rival nations joined forces in space, symbolizing a tentative truce. The mission required extensive coordination, including the development of a universal docking system, the Androgynous Peripheral Attach System, a mechanism still in use today. On July 17, 1975, the Apollo and Soyuz spacecraft docked in orbit. Inside, Thomas Stafford and Alexei Leonov, commanders of their respective crafts, exchanged a historic handshake that heralded a new era of international cooperation. Over the next 44 hours, the crews conducted joint experiments, shared meals, and exchanged gifts. The mission ended with Apollo assisting Soyuz in studying the sun's corona, showcasing how collaboration could advance scientific discovery. The Apollo-Soyuz mission did not just signify the end of the space race. It planted the seeds for future partnerships, including the International Space Station. Building on the success of their Salyut space stations, the Soviet Union launched Mir in 1986. Mir, meaning peace in Russian, became the first modular space station, expanding over a decade with 6 additional modules. Unlike earlier stations, Mir was designed for long-term habitation, hosting cosmonauts and astronauts from around the world. Mir's importance lay not only in its scientific achievements, but also in its symbolic role. It straddled a pivotal moment in history, the dissolution of the Soviet Union. Sergei Krikalev, a cosmonaut aboard Mir during this period, famously left Earth as a Soviet citizen and returned as a Russian. His story underscored the station's role as a microcosm of geopolitical change, orbiting above the divisions on Earth. Throughout its tenure, Mir fostered international collaboration. Astronauts from the United States, Europe, Japan, and even a journalist from Japan visited the station. It became a global laboratory for experiments in microgravity, advancing knowledge in materials, science, medicine. Mir's aging infrastructure presented numerous difficulties. Waste management became an infamous issue, with droplets of frozen urine damaging the station's solar panels. Hygiene concerns mounted as mold grew unchecked in the humid environment. Equipment failures, including computer crashes and a fire in 1997, highlighted the risks of prolonged missions aboard an aging spacecraft. By the late 1990s, maintaining Mir had become unsustainable. The station was decommissioned in 2001, its orbit allowed to decay until it burned up upon re-entry. Despite these challenges, Mir was a resounding success, demonstrating that humans could live and work in space for extended periods. It paved the way for the International Space Station, ISS, where the lessons learned from Mir would be invaluable. As the Soviets expanded their space stations, NASA pursued a bold new vision for space transportation: the Space Shuttle. First envisioned in the late 1960s, the shuttle aimed to revolutionize space travel with a reusable spacecraft capable of routine missions. Unlike the rockets of the Apollo era, which were designed for single use, the shuttle would make space more accessible and cost-effective. The Space Shuttle program officially began with the maiden flight of Columbia on April 12, 1981, the 20th anniversary of Yuri Gagarin's historic journey. The shuttle was a marvel of engineering, blending rocket power with the aerodynamic capabilities of an aircraft. Its design featured 2 solid rocket boosters, a disposable external fuel tank, and an orbiter equipped with wings for atmospheric re-entry. One of the program's most significant innovations was the shuttle's thermal protection system, consisting of over 24,000 silica tiles. These tiles, capable of withstanding temperatures up to 1,260 degrees Celsius, protected the shuttle during the fiery descent through Earth's atmosphere. Despite the system's sophistication, the tiles were fragile and required meticulous inspection and replacement after each mission. The shuttle era brought significant milestones in space exploration. The shuttles deployed satellites, conducted scientific research, and played a critical role in assembling and maintaining the Hubble Space Telescope. In 1990, astronauts aboard Discovery deployed Hubble, a revolutionary instrument that has transformed our understanding of the universe. Subsequent shuttle missions repaired and upgraded Hubble, extending its operational life and enhancing its capabilities. The shuttle program also facilitated international cooperation. It played a vital role in the construction of the ISS, delivering key modules and supplies. Crews from NASA and its international partners used the shuttle to build and maintain the station, solidifying its status as a symbol of global collaboration. Despite its successes, the shuttle program faced devastating setbacks. In 1986, Challenger disintegrated 73 seconds after liftoff, killing all 7 crew members, including teacher Krista McAuliffe, who was set to become the first civilian in space. An investigation revealed that cold temperatures had compromised the integrity of the shuttle's O-rings, leading to the disaster. 17 years later, tragedy struck again with Columbia. During re-entry in 2003, the shuttle disintegrated, killing its 7-member crew. The accident was traced to damage sustained during launch, when foam insulation struck the orbiter's wing. The Columbia disaster prompted a re-evaluation of the shuttle program, ultimately leading to its retirement in 2011. The Space Shuttle program completed 135 missions over 30 years, leaving an indelible mark on space exploration. It demonstrated the feasibility of reusable spacecraft, advanced scientific research, and strengthened international partnerships. However, the program's high costs and inherent risks highlighted the need for new approaches to spaceflight. The shuttle's retirement marked the end of an era, but also the beginning of a new chapter. Private companies like SpaceX and Blue Origin have taken up the mantle, developing reusable rockets and spacecraft that promise to make space travel more accessible and sustainable. The legacy of the shuttle, Mir, and Apollo-Soyuz lives on in the ISS, a testament to what humanity can achieve through cooperation. Orbiting 400 kilometers above Earth, the ISS serves as a laboratory, observatory, and symbol of international unity. Its research spans fields from medicine to climate science, advancing knowledge while inspiring future generations. As humanity looks beyond low Earth orbit, the lessons of the past guide our ambitions. Plans to return to the Moon under NASA's Artemis program aim to establish a sustainable lunar presence, paving the way for crewed missions to Mars. Meanwhile, telescopes like the James Webb Space Telescope will peer deeper into the cosmos, searching for answers to fundamental questions about our origins and place in the universe. The journey of space exploration is far from over. From the first handshake in orbit to the assembly of a global space station, each step forward has brought us closer to realizing the dream of exploring the stars. The challenges are immense, but the spirit of curiosity and cooperation that defined the space race continues to drive humanity toward new horizons. As the 20th century ended, the construction of the International Space Station, ISS, marked the beginning of a new chapter in space exploration. Unlike previous programs driven by rivalry, the ISS was a testament to collaboration. It brought together space agencies from the United States, Russia, Europe, Japan, and Canada, uniting them under a shared vision of exploration and discovery. Since November 2000, the ISS has maintained a continuous human presence in space. The station is far more than an engineering marvel. It is a hub for scientific innovation. Researchers aboard the ISS conduct experiments that are impossible on Earth, leveraging the unique conditions of microgravity to study everything from materials science to human physiology. Understanding the effects of long-term spaceflight on the human body has been a primary focus. Astronauts aboard the ISS have faced challenges such as muscle atrophy, bone density loss, and fluid redistribution, which causes moon face swelling. These studies are critical for preparing humanity for future missions to the Moon, Mars, and beyond. But the ISS has also contributed to practical advancements for life on Earth. Experiments in fluid dynamics have improved medical devices, while research on protein crystallization has led to breakthroughs in drug development. The station has also been pivotal in climate science, offering a unique vantage point to study Earth's atmosphere, weather patterns, and environmental changes. The ISS owes much of its existence to the Space Shuttle program, which ferried modules, supplies, and crew during its operational years. However, the shuttle's retirement in 2011 marked the end of an era. NASA's reliance on the Russian Soyuz spacecraft to transport astronauts to the ISS underscored the complexities of international partnerships. The Soyuz program, with its roots in the Soviet space era, proved its durability and reliability, serving as the world's primary space taxi for nearly a decade. On May 30th, 2020, the United States returned to spaceflight from its own soil with the launch of SpaceX's Crew Dragon spacecraft. The mission, part of NASA's Commercial Crew program, marked a significant shift toward privatization in space exploration. Commercialization has democratized access to space, enabling a broader range of participants, from nations without their own space programs to private researchers and even space tourists. The ISS itself has benefited from this shift, hosting experiments and technologies developed by private companies. This collaboration ensures the station remains a vibrant hub of innovation as its operational life draws to a close. The ISS has served as a testbed for technologies that will enable future deep space missions. From growing food in microgravity to developing closed-loop life support systems, the station has helped solve challenges critical to long-duration space travel. Radiation exposure, a major concern for missions beyond Earth's protective magnetic field, has been studied extensively aboard the ISS, guiding the design of future spacecraft. The station's role as a proving ground is especially vital for NASA's Artemis program, which aims to return humans to the Moon and establish a sustainable presence there by the end of the decade. Lessons learned on the ISS are also informing plans for crewed missions to Mars, a journey that will push the limits of human endurance and engineering. As the ISS approaches the end of its operational life, plans for its decommissioning are underway. By the late 2020s, the station will likely be retired, its orbit allowed to decay until it burns up upon re-entry. This transition will mark the end of an extraordinary chapter in human history, but the legacy of the ISS will endure. The ISS demonstrated what humanity could achieve when working together. It bridged geopolitical divides, fostering collaboration between former adversaries and inspiring a generation of scientists, engineers, and dreamers. Its contributions to science and technology have improved life on Earth and paved the way for humanity's next steps in space. While the ISS represents the pinnacle of orbital exploration, humanity's gaze has always been drawn to more distant horizons. The Artemis program seeks to establish a long-term human presence on the Moon, using it as a stepping stone for Mars and beyond. Lunar missions will focus on building habitats, extracting resources, and refining the technologies needed for deep space travel. Private companies are also playing a crucial role in this vision. SpaceX's Starship, designed for interplanetary travel, is poised to revolutionize the way we explore the solar system. Other firms are developing lunar landers, robotic explorers, and advanced propulsion systems that will make space more accessible than ever before. The story of the ISS and its successors is a story of human ingenuity and perseverance. From the early days of the space race to the cooperative spirit of the ISS, space exploration has shown that our greatest achievements come when we work together. As we prepare to venture further into the cosmos, the lessons of the past will guide us, and the possibilities of the future will inspire us. The Moon, Mars, and the stars beyond beckon us to explore, to discover, and to dream. In the process, we will continue to unlock the secrets of the universe and our place within it. The journey is far from over, and the next chapters of space exploration promise to be just as extraordinary as those that came before. From the confines of Earth's orbit to the vast expanse of deep space, humanity's quest to explore the unknown reflects the best of who we are. A species driven by curiosity, creativity, and a desire to transcend boundaries. Together, we are not just reaching for the stars. We are reaching for a better understanding of ourselves and the universe we call home. By the late 1960s, the Moon had become the ultimate prize in the space race, representing a culmination of technological achievement, national pride, and scientific ambition. The groundwork laid by the Surveyor and Lunar Orbiter programs gave NASA and the United States the tools to move closer to achieving what was once thought impossible: landing humans on another celestial body. While robotic probes explored the Moon's surface and mapped its terrain in remarkable detail, the next challenge was sending astronauts to the lunar surface and bringing them back safely. The Apollo program emerged as America's answer to this challenge. Fueled by President John F. Kennedy's bold declaration in 1961, "We choose to go to the Moon in this decade," NASA funneled resources, ingenuity, and manpower into the ambitious project. Apollo wasn't just about beating the Soviets. It was about redefining humanity's relationship with space and proving that human ingenuity could overcome even the most daunting challenges. The first missions of the Apollo program focused on testing the spacecraft, rocket systems, and procedures needed for a moon landing. Apollo 1, tragically, ended in disaster during a routine ground test in January 1967, when a cabin fire claimed the lives of astronauts Gus Grissom, Ed White, and Roger B. Chaffee. The tragedy underscored the inherent risks of space exploration and forced NASA to re-examine its designs and protocols. The setback didn't deter NASA, which redoubled its efforts to honor the fallen crew by achieving their shared dream. Apollo 7, the program's first crewed mission in 1968, proved the redesigned command module could operate safely in Earth's orbit. This success paved the way for Apollo 8, a mission that marked a historic milestone. On December 21, 1968, Apollo 8 launched from Kennedy Space Center, carrying astronauts Frank Borman, Jim Lovell, and Bill Anders. It became the first crewed spacecraft to leave Earth's orbit and travel to the Moon. Over the course of the mission, the crew completed 10 orbits around the Moon, capturing breathtaking views of the lunar surface and Earth rising above the Moon's horizon. The famous Earthrise photograph, taken by Anders, became a symbol of the fragility of our planet and humanity's unity. For the first time, people saw Earth not as a collection of nations, but as a singular, delicate home, suspended in the vastness of space. Apollo 8's success brought the world closer to realizing the dream of landing on the Moon. On July 16, 1969, the world watched as Apollo 11 launched atop the powerful Saturn V rocket, the most complex and capable machine of its time. Astronauts Neil Armstrong, Buzz Aldrin, and Michael Collins were on a mission to make history. After a 4-day journey, their spacecraft entered lunar orbit, setting the stage for the ultimate challenge: landing on the Moon. The lunar module, Eagle, descended to the Moon's surface on July 20, 1969. With Armstrong and Aldrin aboard, the module's computer alarms signaled potential problems as it neared the landing site. Armstrong, piloting manually, guided Eagle past a rocky area to a smooth plain in the Sea of Tranquility. As the module touched down, Armstrong radioed back to Mission Control. "Houston, Tranquility Base here. The Eagle has landed." 6 hours later, Armstrong descended the module's ladder, stepping onto the Moon's surface and uttering the immortal words, "That's one small step for man, one giant leap for mankind." Aldrin followed, and together they spent over 2 hours exploring the surface, collecting samples, and setting up experiments. The moment was broadcast live to an estimated 600 million viewers worldwide, uniting humanity in awe and inspiration. The Apollo program wasn't just about national prestige, it was also a groundbreaking scientific endeavor. Over 6 missions, from Apollo 11 to Apollo 17, astronauts brought back 382 kilograms of lunar rock and soil samples, offering unprecedented insights into the Moon's history and composition. These samples revealed that the Moon was geologically active in its early history and provided clues about the conditions of the early solar system. Apollo missions also deployed a series of scientific instruments on the lunar surface, collectively known as the Apollo Lunar Surface Experiments Package, ALSEP. These experiments measured seismic activity, studied the Moon's magnetic field, and tracked heat flow from its interior. Data collected from ALSEP revolutionized our understanding of the Moon and laid the groundwork for future exploration. The Apollo program's final mission, Apollo 17, launched in December 1972. It marked the end of an era, but also the beginning of a new chapter in humanity's exploration of space. Commander Gene Cernan, the last astronaut to leave the lunar surface, famously said, "We leave as we came, and, God willing, as we shall return, with peace and hope for all mankind." The program's legacy endures not only in the scientific discoveries it enabled, but also in its profound impact on humanity's perspective. Apollo showed that exploration could unify a world divided by Cold War tensions, inspiring generations to dream big and push the boundaries of what's possible. Even after the end of Apollo, the Moon continued to captivate scientists and explorers. Robotic missions from countries like China, India, and Japan have expanded our knowledge of the lunar surface, uncovering resources such as water ice in permanently shadowed craters at the poles. These discoveries have renewed interest in the Moon as a potential base for future exploration. NASA's Artemis program, named after Apollo's twin sister in Greek mythology, aims to return humans to the Moon by 2025. With an emphasis on sustainability, Artemis will establish a long-term presence on the lunar surface, serving as a stepping stone for crewed missions to Mars. The program will rely on cutting-edge technologies, such as reusable spacecraft and advanced habitats, to ensure the success of this ambitious endeavor. The Moon's proximity to Earth makes it an ideal testing ground for technologies and systems needed for deep space exploration. Future missions will focus on harvesting lunar resources, such as water for drinking, oxygen, and rocket fuel. These capabilities will enable humanity to explore further into the solar system while reducing reliance on supplies from Earth. Private companies are also playing a critical role in the new lunar age. This collaboration between government agencies and private industry marks a new era of innovation and partnership in space exploration. The Moon, our closest celestial neighbor, has been a source of wonder and inspiration for millennia. From ancient myths to the bold steps of Apollo, its story is intertwined with humanity's own. As we prepare to return, the Moon promises to unlock new knowledge, spark innovation, and bring us closer to the stars. The dream of the Moon is no longer just about reaching it. It's about building a future where humanity can thrive beyond Earth. By returning to the Moon, we take another giant leap, not only for ourselves, but for generations to come, as we continue the journey into the vast unknown. On December 24, 1968, Apollo 8 entered lunar orbit, marking the first time humans had ever traveled so far from Earth. Astronauts Frank Borman, James Lovell, and William Anders became pioneers of a journey that required precision, courage, and groundbreaking technology. As Apollo 8 circled the far side of the Moon, the crew lost radio contact with mission control for 34 tense minutes. When communication was re-established, a calm voice from space confirmed their success. "Houston, please be informed. There is a Santa Claus." Humanity had reached another world. During their 10 lunar orbits, the crew conducted the first-ever close-up reconnaissance of the Moon's surface. They captured stunning images of craters and mountains, but the most impactful photograph was one they had not planned to take. Anders's Earthrise image, a vibrant blue Earth rising above the stark, lifeless lunar horizon, transfixed the world. It provided a profound reminder of our planet's fragility and unity, inspiring environmental and philosophical movements for decades to come. After the success of Apollo 8, NASA turned its attention to perfecting the hardware and maneuvers required for a lunar landing. Apollo 9, launched in March 1969, tested the lunar module LM in Earth orbit. This mission confirmed the LM's ability to separate from the command module, perform engine burns, and dock safely. It was the first true test of the spacecraft that would carry humans to the Moon's surface. 2 months later, Apollo 10 served as the dress rehearsal for the landing itself. The mission took astronauts Thomas Stafford, John Young, and Eugene Cernan within 15 kilometers of the lunar surface, practicing critical maneuvers and gathering detailed photographic data. On July 16, 1969, Apollo 11 launched from Kennedy Space Center with astronauts Neil Armstrong, Buzz Aldrin, and Michael Collins aboard. The mission captivated the world, its significance transcending political and cultural boundaries. After a 4-day journey, the spacecraft entered lunar orbit, and Armstrong and Aldrin prepared for their historic descent to the surface in the lunar module, Eagle. The descent was not without challenges. As Eagle approached the Moon, Armstrong realized the planned landing site was strewn with boulders. With just seconds of fuel remaining, he manually piloted the craft to a safer location, touching down in the Sea of Tranquility. Armstrong's calm announcement, "Houston, Tranquility Base here. The Eagle has landed," signaled humanity's first arrival on another world. 6 hours later, Armstrong stepped onto the lunar surface, becoming the first human to walk on the Moon. His words, "That's one small step for man, one giant leap for mankind," captured the monumental nature of the achievement. Aldrin soon followed, describing the landscape as a magnificent desolation. The pair spent over 2 hours exploring, collecting samples, and deploying scientific instruments, while Collins remained in orbit aboard the command module Columbia. The moonwalk ended as the astronauts planted an American flag and left behind a plaque reading, "We came in peace for all mankind." Apollo 11's safe return to Earth on July 24, 1969, marked the completion of humanity's most audacious technological feat to date. Apollo 11 was only the beginning of a series of missions that would expand humanity's knowledge of the Moon. These samples revealed the Moon's volcanic past, the composition of its crust, and evidence of ancient collisions with asteroids and comets. Apollo astronauts deployed a variety of scientific instruments, including seismometers that measured moonquakes and heat flow sensors that studied the Moon's internal structure. The data confirmed that the Moon, unlike Earth, lacks a molten core and tectonic activity. One of the program's most unexpected findings came from Apollo 17, which discovered traces of orange soil near the landing site. Analysis revealed that the soil was formed during volcanic activity billions of years ago, offering clues about the Moon's early history and evolution. Beyond its scientific achievements, Apollo transformed humanity's perception of itself. The missions united a world often divided by conflict, demonstrating what was possible through cooperation, determination, and innovation. The astronauts became global icons, embodying the potential of human ingenuity and courage. The sight of Earth from the Moon inspired a new sense of environmental awareness, contributing to the birth of modern environmental movements. For many, Apollo's greatest legacy was its reminder of our shared humanity and the fragile beauty of our home planet. With the conclusion of Apollo in 1972, human exploration of the Moon paused, but the desire to return never faded. In the decades that followed, robotic missions from countries including the United States, China, and India continued to study the Moon. These probes revealed new details about its composition, topography, and resources, particularly the discovery of water ice in permanently shadowed craters at the lunar poles. The Moon's water reserves are a game-changer for future exploration, offering a potential source of drinking water, oxygen, and rocket fuel. These findings have reignited interest in establishing a sustainable human presence on the Moon. NASA's Artemis program, named after Apollo's twin sister in Greek mythology, aims to return humans to the Moon by 2025. Unlike Apollo, Artemis seeks to establish a long-term presence, with the goal of enabling future missions to Mars. Artemis missions will focus on the Moon's south pole, where water ice could provide critical resources for habitation and exploration. The program represents a new era of collaboration, with contributions from international partners and private companies. Artemis will also prioritize diversity, ensuring the first woman and the first person of color set foot on the lunar surface. The Moon is more than a destination. It is a gateway to the stars. By mastering the challenges of living and working on the Moon, humanity will gain the knowledge and experience needed to venture further into the solar system. The lessons learned from Apollo and Artemis will shape the next phase of exploration, from missions to Mars to the eventual colonization of other worlds. The Moon has captivated humanity for millennia, inspiring myths, art, and scientific inquiry. From the first robotic probes to the footsteps of Apollo astronauts, it has been a symbol of human ambition and ingenuity. As we prepare to return with Artemis, the Moon remains a source of wonder and a reminder of what we can achieve together. The journey to the Moon is far from over. It is a story of discovery, courage, and the enduring human spirit. A story that continues to unfold as we reach for the stars. For the astronauts, the return to Earth was as surreal as their journey to the Moon. They were quarantined for 3 weeks aboard the USS Hornet, and later in a specialized facility to ensure no harmful lunar pathogens could affect Earth's environment. And world leaders extended their congratulations, acknowledging the global significance of the achievement. Apollo 11 wasn't just about planting a flag. It was a mission steeped in science. The experiments and samples brought back by Armstrong and Aldrin transformed humanity's understanding of the Moon. Among the most notable was the deployment of retroreflectors, which continue to provide precise measurements of the Moon's distance from Earth. The collected lunar rocks, totaling 21.6 kilograms, were another key accomplishment. These samples revealed the Moon's volcanic history and confirmed its origin as a fragment of Earth, created during a colossal impact billions of years ago. Scientists also found that the Moon was geologically inactive, with no evidence of plate tectonics or a molten core. The instruments left behind, such as seismometers, recorded moonquakes caused by tidal forces and meteorite impacts, providing invaluable data about the Moon's interior. These contributions established a foundation for decades of lunar research and continue to shape modern planetary science. While the United States celebrated its lunar victory, the Soviet Union quietly stepped back from its human lunar exploration program. The loss of the Luna 15 probe during Apollo 11's mission underscored the challenges of soft landing on the Moon, even with robotic spacecraft. The Soviets shifted focus to other areas of space exploration, achieving milestones such as the first space station, Salyut 1, and pioneering long-duration missions in low Earth orbit. Apollo 11 also marked the peak of Cold War-era space exploration, With the United States firmly establishing dominance in the space race, public interest in lunar missions began to wane. The enormous cost of the Apollo program, approximately $25 billion, over $150 billion today, led to its eventual wind-down after Apollo 17 in 1972. Apollo 11's legacy extends far beyond the scientific and technological. The mission profoundly shaped humanity's perception of itself and its place in the cosmos. For the first time, the world saw Earth as a fragile, interconnected pale blue dot suspended in the vastness of space. This perspective inspired the modern environmental movement, emphasizing the need to protect our shared home. The mission also demonstrated the power of human ingenuity and collaboration. The Apollo program brought together more than 400,000 engineers, scientists, and technicians, proving that extraordinary feats are possible when people work together toward a common goal. For many, Apollo 11 symbolized hope and progress during a turbulent era marked by geopolitical tensions, civil rights struggles, and the Vietnam War. It was a unifying moment that transcended borders and reminded the world of the boundless potential of human creativity. While Apollo 11 was a monumental achievement, it was only the beginning of humanity's exploration of the Moon. Subsequent Apollo missions continued to expand our knowledge, with Apollo 12, 14, 15, 16, and 17 achieving increasingly ambitious scientific goals. From the discovery of volcanic plains to the exploration of lunar mountains and valleys, these missions demonstrated the Moon's complexity and scientific richness. However, the conclusion of Apollo 17 marked the end of crewed lunar exploration for decades. In the following years, robotic missions from various countries continued to study the Moon, uncovering new details about its surface and resources. The discovery of water ice at the lunar poles in the 1990s reignited interest in returning to the Moon, as these resources could support future human missions and even serve as fuel for deep space exploration. In the 21st century, the Moon has once again become a focal point for space exploration. NASA's Artemis program aims to return humans to the lunar surface by 2025, building on the legacy of Apollo while advancing modern technology. Unlike the earlier missions, Artemis focuses on sustainability, with plans to establish a long-term presence at the Moon's South Pole. The Artemis program will feature diverse crews, including the first woman and the first person of color to set foot on the Moon. It will also emphasize international collaboration, with contributions from agencies like the European Space Agency, Japan's JAXA, and private companies like SpaceX. The Moon remains a vital stepping stone for humanity's ambitions beyond Earth. Its proximity allows for testing new technologies, conducting groundbreaking research, and building the infrastructure needed for deeper exploration. By mastering the challenges of lunar exploration, humanity is preparing for the next great leap. Mars. The story of Apollo 11 is not just one of technological achievement, but also of inspiration. As we look to the future, the lessons of Apollo guide us, and the Moon continues to beckon as a symbol of what is possible when we reach for the stars. From the first footsteps in 1969 to the Artemis missions of today, the Moon represents humanity's drive to explore, to learn, and to push the boundaries of what we can achieve together. The journey continues, and the best is yet to come. Apollo 17 marked the culmination of NASA's ambitious lunar program. As the last crewed mission to the Moon, it carried the weight of concluding an era of exploration while laying the foundation for future scientific discoveries. Commander Gene Cernan and geologist Harrison Schmitt spent 3 days on the lunar surface, pushing the boundaries of what could be achieved in lunar science. They collected over 110 kilograms of lunar material, more than any other mission, and conducted detailed geological surveys of the Taurus-Littrow Valley. Harrison Schmitt, the first professional scientist to travel to the Moon, brought a unique approach to the mission. His expertise transformed the Apollo program's scientific capabilities, enabling precise identification of significant geological features. One of the most remarkable finds was a sample of orange soil, later revealed to be volcanic glass, formed during an ancient eruption over 3 billion years ago. This discovery provided invaluable insights into the Moon's volcanic activity and its evolution as a celestial body. Apollo 17 showcased the full potential of the lunar rover, allowing the crew to traverse nearly 35 kilometers of challenging terrain. This remarkable vehicle enabled astronauts to reach areas previously inaccessible, expanding the scope of exploration far beyond earlier missions. The rover became a vital tool for collecting diverse samples and conducting experiments, cementing its place as one of the program's most significant innovations. The Taurus-Littrow site was chosen for its diverse geological features, including steep slopes and boulder-strewn plains. Cernan and Schmitt explored regions shaped by ancient volcanic activity and asteroid impacts, uncovering evidence of the Moon's complex history. Their findings, combined with data from previous missions, provided a more complete picture of the Moon's origin and its relationship to Earth. On December 14, 1972, after over 3 days of exploration, Cernan and Schmitt prepared to leave the lunar surface. Before boarding the lunar module, Cernan delivered a heartfelt message. "We leave as we came, and, God willing, as we shall return, with peace and hope for all mankind." These words captured the spirit of Apollo and the aspirations of humanity to continue its journey into the cosmos. As the lunar module ascended, the astronauts left behind a plaque inscribed with the names of all 12 men who had walked on the Moon. The legacy of their work remained etched into the lunar surface, a testament to human ingenuity and determination. The Apollo program revolutionized our understanding of the Moon and its role in the solar system. Instruments deployed during Apollo missions, such as seismometers and retroreflectors, continued to transmit data long after the astronauts returned home. Moonquakes detected by these instruments provided valuable insights into the Moon's internal structure, while laser experiments confirmed that the Moon is slowly drifting away from Earth at a rate of 3.8 centimeters per year. These findings not only advanced lunar science, but also deepened our understanding of planetary formation and evolution. The Apollo program was not without its challenges, from the tragic loss of the Apollo 1 crew to the harrowing survival story of Apollo 13. Every mission carried immense risks. Engineers and scientists worked tirelessly to overcome these obstacles, developing technologies and procedures that continue to shape space exploration today. One recurring issue was the pervasive lunar dust. Fine and abrasive, it clung to spacesuits, tools, and equipment, causing wear and tear. Apollo astronauts often described it as smelling like gunpowder and being incredibly difficult to clean. Addressing this challenge became a priority for future missions, as lunar dust posed risks to both machinery and human health. After Apollo 17, NASA shifted its focus to Earth-orbiting missions and the development of the Skylab space station. The cost of the Apollo program, coupled with waning public interest, led to the cancellation of additional lunar missions. Skylab provided a platform for extended human presence in space, building on the lessons learned during Apollo. Experiments conducted aboard Skylab helped scientists better understand the effects of long-duration spaceflight on the human body, paving the way for future endeavors in low Earth orbit and beyond. The Apollo program's impact extends far beyond its scientific and technological achievements. It inspired generations of engineers, scientists, and dreamers to pursue careers in space exploration. The iconic images of Earthrise and astronauts standing on the Moon fostered a sense of global unity, reminding humanity of its shared home and the possibilities of collective effort. The program also laid the groundwork for international collaboration in space. The partnerships forged during the Apollo-Soyuz test project and later missions set the stage for the International Space Station, a symbol of cooperation among nations. The Moon remains central to humanity's exploration ambitions. NASA's Artemis program aims to return humans to the lunar surface by the mid-2020s, with the goal of establishing a sustainable presence. Artemis will focus on the Moon's south pole, where water ice could provide critical resources for future missions. Unlike Apollo, Artemis emphasizes diversity and collaboration, with plans to include international partners and private companies. The program will also feature the first woman and the next man to walk on the Moon, reflecting the inclusive spirit of modern exploration. Apollo 17 closed one chapter in the story of space exploration, but it also marked the beginning of another. The knowledge and experience gained during those missions continue to inform and inspire today's efforts to explore the Moon, Mars, and beyond. As humanity prepares to return to the lunar surface, the lessons of Apollo serve as a reminder of what can be achieved through courage, innovation, and determination. The Moon, our closest celestial neighbor, remains a beacon of wonder and discovery. From the first footprints in the Sea of Tranquility to the bold ambitions of Artemis, the journey continues, a testament to humanity's unyielding desire to reach for the stars. As humanity transitions from the era of the Apollo program into a more globally collaborative and technologically advanced age, the Moon remains at the forefront of exploration. The discovery of water ice and advances in robotic technology have transformed our perception of the Moon, from a distant goal of competition to a vital stepping stone for humanity's future in the solar system. The Moon, once a stage for geopolitical rivalry, is now a shared arena for government agencies and private industry. Space exploration, particularly lunar exploration, has entered a new chapter where collaboration is key. Private companies are developing lunar landers and rovers, while national space agencies provide funding, expertise, and infrastructure. This partnership aims to make regular Moon missions not only feasible, but also sustainable. Access to the Moon's resources, particularly water ice, is central to this ambition. Extracting water from lunar craters and polar regions could provide life support for long-term human habitation and serve as a source of hydrogen and oxygen for rocket fuel. This innovation would significantly reduce the cost of deeper space missions, transforming the Moon into a critical hub for interplanetary travel. Robotic missions have taken center stage in this new era, performing reconnaissance and laying the groundwork for human return. China's Yutu-2, delivered by the Chang'e 4 mission, became the first rover to explore the Moon's far side. Operating in the Aitken Basin, one of the oldest and largest impact craters in the solar system, U-22 has unveiled geological mysteries, including the unexpected discovery of relatively young rocks in a region shaped by ancient impacts. Such findings challenge previous assumptions about the Moon's history and open new questions about its geological evolution. Similarly, NASA's Lunar Reconnaissance Orbiter, LRO, launched in 2009, has provided high-resolution maps of the lunar surface, identifying potential landing sites and points of interest for future missions. Equipped with radar, infrared imaging, and powerful cameras, the LRO has become an invaluable tool for lunar science, continuously collecting data that aids both government and commercial ventures. India's Chandrayaan-1, launched in 2008, further advanced our understanding of the Moon. Its instruments confirmed the presence of water ice and revealed that the Moon was once entirely molten. Chandrayaan-1's groundbreaking discoveries underscored the Moon's potential as a resource-rich frontier, reigniting global interest in lunar exploration. The discovery of water ice in permanently shadowed craters near the Moon's poles is a game-changer for space exploration. These reservoirs of ice, hidden in the dark depths of the lunar surface, offer the promise of self-sufficiency for future missions. Water can be split into hydrogen and oxygen, providing breathable air and rocket fuel. This capability would enable not only longer stays on the Moon, but also more affordable missions to Mars and beyond. Water ice on the Moon has transformed how spacefaring nations and private companies view the lunar surface. The Moon is no longer just a destination. It is a launch pad for humanity's expansion into the solar system. As companies and governments compete to stake their claim on these resources, the Moon's role as a gateway to deep space becomes increasingly apparent. The vision for lunar exploration has shifted from one-off missions to sustained presence. NASA's Artemis program, set to return humans to the Moon by the mid-2020s, embodies this vision. The program aims to establish a long-term human presence on the Moon, focusing on the South Pole's ice-rich regions. Unlike Apollo, Artemis emphasizes international collaboration, with contributions from partners like the European Space Agency, Japan's JAXA, and private companies. Artemis will also showcase diversity, with plans to include the first woman and the next man to set foot on the lunar surface. These missions will test new technologies, develop infrastructure, and create a foundation for deeper space exploration. Lunar habitats, power systems, and mining technologies will be tested to ensure that humans can live and work on the Moon sustainably. Private companies have become vital players in this new era of lunar exploration. SpaceX, Blue Origin, and other aerospace firms are designing reusable rockets and lunar landers to reduce the cost of access to space. By leveraging commercial capabilities, space agencies can focus on scientific research and exploration while relying on private industry for transportation and logistics. The lunar economy is no longer a distant dream. Companies are exploring the potential for mining helium-3, a rare isotope that could be used for nuclear fusion, as well as extracting rare earth elements and building materials from the lunar regolith. These ventures promise to unlock the Moon's economic potential, creating opportunities for technological innovation and economic growth. The Moon's proximity to Earth and its abundant resources make it the ideal stepping stone for Mars exploration. Lunar missions provide a testing ground for technologies that will be critical for surviving on Mars, such as closed-loop life support systems, in-situ resource utilization, and habitat construction. Lessons learned on the Moon will inform the design of Mars missions, from surface operations to long-duration space travel. By establishing a sustainable presence on the Moon, humanity can build the infrastructure needed to support missions to Mars and beyond. Lunar bases could serve as refueling stations, enabling spacecraft to carry less fuel from Earth and reducing mission costs. The Moon's low gravity also makes it an efficient launch point for deep space missions. The future of lunar exploration is one of collaboration, both between nations and with private industry. The Lunar Gateway, a planned space station in lunar orbit, will serve as a hub for international missions, supporting scientific research and technology development. This spirit of cooperation reflects a broader shift in space exploration, where shared goals and resources enable greater achievements. As humanity looks to the Moon, the lessons of Apollo and the advances of robotic exploration guide the way. The Moon, once a symbol of Cold War competition, is now a beacon of unity and possibility. It represents not just our past achievements, but also our future potential to explore, innovate, and thrive beyond Earth. The Moon's role in humanity's story is far from over. From robotic pioneers to human settlers, the next chapter of lunar exploration promises to unlock new knowledge, resources, and opportunities. As we build a sustainable presence on the Moon, we take the first steps toward becoming a multi-planetary species. The Moon is no longer just a destination. It is a gateway to the stars, a testament to human ingenuity and ambition. Our journey continues, and the Moon remains a constant companion, guiding us toward a future of exploration and discovery. From its dusty craters to its shadowed poles, the Moon holds the promise of a new era. One where humanity's reach extends beyond the Earth, fueled by curiosity, collaboration, and courage. Mariner 2's revelations about Venus forever altered humanity's understanding of the planet. Rather than oceans or swamps, Venus was unveiled as a hellish world, shrouded in a dense atmosphere of carbon dioxide and sulfuric acid clouds. The surface temperature was measured to exceed 460 degrees Celsius, 860 degrees Fahrenheit, hot enough to melt lead. These findings challenged earlier hopes of a habitable twin to Earth and set a precedent for future missions to uncover the secrets of our planetary neighbors. The data from Mariner 2 revealed that Venus's atmosphere traps heat through an extreme greenhouse effect, a phenomenon that has become critical to our understanding of planetary climates, including our own. Venus serves as a cautionary tale of what can happen when greenhouse gases accumulate unchecked. It is a mirror for Earth, showing us the devastating effects of a runaway greenhouse effect and underscoring the fragility of our own environment. Following Mariner 2's success, the Soviet Union launched the Venera program, a series of probes dedicated to Venus exploration. Venera 7 became the first spacecraft to transmit data from the surface of another planet in 1970. While the mission lasted only 23 minutes before succumbing to Venus's extreme heat and pressure, it marked a milestone in interplanetary exploration. Subsequent Venera missions improved on their predecessors, providing increasingly detailed data. Venera 9 and 10 returned the first black and white images of Venus's rocky terrain, revealing a desolate landscape shaped by volcanic activity. The Soviet program achieved breakthroughs in spacecraft design, developing robust systems capable of surviving Venus's hostile conditions for longer durations. NASA also contributed to our understanding of Venus with the Pioneer Venus project in 1978. This consisted of 2 spacecraft, an orbiter to map Venus's atmosphere and surface, and a multi-probe mission that descended through the atmosphere, gathering data on its composition and dynamics. Pioneer Venus provided comprehensive insights into the planet's complex weather systems, including powerful winds circulating at speeds of over 360 kilometers per hour, 224 miles per hour. Despite the wealth of data from earlier missions, much of Venus remained a mystery due to its opaque clouds. In the 1990s, NASA's Magellan spacecraft finally pierced this veil. Using advanced radar imaging, Magellan mapped 98% of Venus's surface with remarkable detail. The data revealed a planet dominated by volcanic plains, massive mountain ranges, and vast plateaus. Evidence suggested that Venus might still be volcanically active, with some features showing signs of relatively recent eruptions. Magellan's findings also highlighted the differences between Venus and Earth. Unlike our planet, Venus lacks plate tectonics, a critical process for recycling heat and maintaining a stable climate over geological time. Instead, heat builds up beneath Venus's crust, periodically releasing through catastrophic resurfacing events that may cover vast areas of the planet with fresh lava flows. Venus's study continues to provide valuable lessons for Earth science, particularly in understanding climate change. Its atmosphere, composed of over 96% carbon dioxide, is an extreme example of the greenhouse effect, offering a glimpse into a potential future for Earth if carbon emissions remain unchecked. Venus also challenges scientists to reconsider planetary habitability. Despite its current harsh conditions, some researchers speculate that Venus may have once been more Earth-like, with liquid water oceans and a temperate climate billions of years ago. What caused this dramatic transformation remains a central question in planetary science. Venus also pushes the boundaries of spacecraft engineering. The planet's extreme environment demands innovative solutions to withstand its crushing pressure, corrosive atmosphere, and intense heat. These technological challenges have spurred advances in materials, science, robotics, and remote sensing that benefit a wide range of industries beyond space exploration. Today, interest in Venus is experiencing a revival. NASA's Veritas and Da Vinci Plus missions, set to launch in the late 2020s, aim to unravel the mysteries of Venus's geology and atmosphere. Veritas, Venus emissivity, radio science, INSAR, topography, and spectroscopy, will create high-resolution maps of Venus's surface, searching for evidence of active tectonics and volcanism. Da Vinci Plus, deep atmosphere Venus investigation of noble gases, chemistry, and imaging, will plunge through Venus's atmosphere, analyzing its composition and capturing detailed images of its surface during descent. These missions represent a new era of Venus exploration, building on decades of scientific inquiry and technological innovation. By studying Venus in greater detail, scientists hope to answer fundamental questions about planetary evolution, climate systems, and the conditions necessary for habitability. While Venus captivates as our nearest neighbor, it is just one piece of the solar system's intricate puzzle. The insights gained from Venus missions inform our broader exploration of terrestrial planets, helping us understand the processes that shape their environments. These lessons are invaluable as we prepare for more ambitious journeys, from robotic missions to the moons of Jupiter and Saturn, to human exploration of Mars. As humanity ventures further into space, each mission builds upon the knowledge and achievements of the past. Venus, with its challenges and enigmas, serves as a reminder of both the difficulties and rewards of exploration. Its study not only deepens our understanding of the cosmos, but also reflects our enduring quest to push the boundaries of what is possible. The exploration of Venus is a testament to human ingenuity and curiosity. It demonstrates our ability to overcome formidable challenges and adapt to the unknown. As we continue to study Venus, we are not just learning about a neighboring world, we are learning about ourselves. The knowledge gained from these missions shapes our understanding of the universe and our place within it, inspiring future generations to reach for the stars. Venus, once shrouded in mystery, now stands as a beacon of discovery. Its lessons guide us as we look outward, toward Mars, the icy moons of the outer planets, and eventually, the stars. The journey to Venus is part of a greater story, one of exploration, innovation, and the unyielding human spirit. From the first flybys to the cutting-edge missions of today, Venus remains a symbol of humanity's determination to uncover the secrets of the cosmos and forge a path toward the unknown. The exploration of Venus has transformed our understanding of planetary evolution and climate extremes. Once thought to be Earth's twin, Venus reveals a dark mirror of what might become of our home planet under unchecked environmental changes. The more we learn about this inhospitable world, the more it serves as both a cautionary tale and a reminder of Earth's fragility. NASA's Magellan mission marked a turning point in Venusian exploration, giving us the first detailed maps of its surface. Using radar to pierce Venus's dense atmosphere, Magellan revealed a landscape dominated by volcanic plains, immense lava flows, and deformed mountain ranges. Among its findings were massive shield volcanoes and coronae, circular formations created by upwellings of magma. These features underscored Venus's geological activity, suggesting a world that is far from dead. Venus's surface is not just hostile, it is downright alien. With temperatures reaching 475 degrees Celsius, 900 degrees Fahrenheit, and atmospheric pressures equivalent to being 900 meters underwater, it is an environment that defies imagination. Magellan revealed that Venus's volcanoes are not only widespread, but might still be active, creating a surface that constantly changes in some regions. However, unlike Earth, Venus lacks tectonic plates, the geologic mechanisms that recycle rock and regulate our planet's internal heat. Instead, Venus seems to undergo periodic, catastrophic resurfacing events, where heat builds up and is released in planet-wide volcanic outpourings. These findings suggest that Venus's early history might have been strikingly different from its current state. Billions of years ago, Venus could have had liquid water oceans and a more temperate climate, much like Earth. But its closer proximity to the Sun sealed its fate. Over time, the Sun's radiation caused Venus's water to evaporate into the atmosphere, where sunlight split the water molecules into hydrogen and oxygen. The lightweight hydrogen escaped into space, leaving behind an atmosphere increasingly dominated by carbon dioxide. This set off a runaway greenhouse effect, turning the planet into the searing furnace we see today. The story of Venus is not just a tale of planetary science, it is a warning. As the Sun ages and grows brighter, Earth's climate could similarly become inhospitable if greenhouse gas levels rise unchecked. Venus offers a glimpse of a worst-case scenario, where natural processes and external influences combine to create an unlivable world. For scientists, Venus is a laboratory to study climate change on a planetary scale, yielding insights that could help us protect our own planet. But Venus is not just a lesson in what can go wrong. It also challenges us to think about how life could adapt to extreme environments. While the surface is a hellscape, the upper atmosphere, about 50 kilometers above the ground, offers more temperate conditions. Here, temperatures and pressures are closer to those on Earth's surface, raising intriguing possibilities about whether microbial life could exist in Venus's clouds. The recent detection of phosphine, a chemical that could be linked to biological processes, has reignited interest in this question, though the findings remain debated. Venus has shaped our approach to planetary exploration in profound ways. The challenges posed by its environment have driven advances in spacecraft engineering, materials science, and remote sensing technology. From the Soviet Venera program to NASA's Magellan mission, each success and failure has taught us how to design probes capable of withstanding extreme conditions. These innovations have applications far beyond Venus, informing missions to other harsh environments in the solar system, from Jupiter's moons to the icy reaches of the Kuiper Belt. The exploration of Venus has also been a proving ground for international collaboration. The European Space Agency's Venus Express, launched in 2005, conducted a detailed study of Venus's atmosphere, confirming the planet's dynamic weather systems and volcanic activity. Meanwhile, Japan's Akatsuki spacecraft, currently in orbit, continues to monitor Venus's complex climate, providing new insights into its atmospheric circulation and cloud formations. The renewed interest in Venus has inspired a new wave of missions, each aiming to answer unresolved questions about the planet's history and potential for life. NASA's upcoming Da Vinci Plus mission will dive into Venus's atmosphere, analyzing its composition and capturing high-resolution images of its surface during descent. Meanwhile, Veritas will create detailed topographic maps, searching for signs of current geological activity and providing clues about the planet's past. These missions are not just about Venus. They are about understanding the broader processes that shape rocky planets, including Earth. By studying Venus, scientists hope to refine models of planetary evolution and better predict the conditions that could make a planet habitable or uninhabitable. This knowledge is critical as we search for life beyond our solar system and consider the long-term future of humanity. As we look to the stars, Venus reminds us of the importance of sustainable exploration. The knowledge gained from studying its extremes will inform not only our understanding of the cosmos, but also our approach to preserving Earth's environment. Venus challenges us to confront the consequences of climate change while inspiring us to push the boundaries of what is possible in space exploration. The harsh lessons of Venus have far-reaching implications for humanity's future. They reinforce the need for international cooperation in addressing global challenges and advancing scientific discovery. Venus's story is a testament to our ability to learn from the universe and adapt to its challenges, demonstrating the resilience and ingenuity of human curiosity. Venus remains one of the solar system's greatest enigmas, a planet that holds both the promise of answers and the peril of warnings. It is a world that forces us to reflect on our own place in the cosmos, to consider the fragility of our planet and the resilience of our species. As we continue to explore Venus, we are not just uncovering the secrets of a distant world. We are discovering the limits of human potential and the endless possibilities of the universe. From the early missions of Mariner and Venera to the cutting-edge explorations of today, Venus stands as a symbol of both the challenges and rewards of space exploration. It reminds us that even in the most inhospitable environments, there is much to learn, and that in seeking to understand the unknown, we come to understand ourselves. Venus, with its fiery landscapes and haunting mysteries, calls us to look upward, to dream, and to strive for a future that honors both our planet and our potential. The images and data from NASA's Messenger mission confirmed a startling reality. Mercury is shrinking. As the planet's core cools over billions of years, the surrounding material contracts, causing the surface to wrinkle and crack. This process has created immense cliffs, known as scarps, that stretch for hundreds of kilometers and rise several kilometers high. These features are like wrinkles on the skin of an aging planet, offering a glimpse into Mercury's geological evolution and the forces at work deep within its interior. Mercury's shrinkage is not only a testament to its dynamic history, but also a key to understanding the early solar system. The planet's immense density and oversized core suggest it experienced a unique formation process. Messenger's data revealed that Mercury's surface is rich in volatile elements such as sulfur and potassium, elements that would have evaporated if the planet had endured the scorching heat of the sun during its early development. This discovery challenges previous theories about the planet's origin and raises questions about the diversity of planetary formation processes. One of Messenger's most groundbreaking findings was evidence of water ice and organic materials in permanently shadowed craters near Mercury's poles. Despite the planet's searing daytime temperatures exceeding 400 degrees Celsius, the depths of these craters remain in eternal darkness, creating cold traps where temperatures plunge below -200 degrees Celsius. These frigid pockets have preserved water ice for billions of years, likely delivered by comets and asteroids during the early bombardment period of the solar system. The discovery of water ice on Mercury is a paradox that highlights the extremes of the innermost planet. While the sun relentlessly scorches its surface, these hidden reservoirs in the shadowed craters offer a glimpse of the delicate interplay between planetary geology and solar influence. Studying these icy deposits not only reveals clues about Mercury's history, but also enhances our understanding of the distribution of water throughout the solar system, a critical factor in the search for life. Messenger's mission also unveiled Mercury as a world shaped by intense volcanic activity. Vast plains of ancient lava flows cover large portions of its surface, evidence of a time when the planet's interior was far more active. These lava flows buried many older impact craters, leaving behind ghost craters, faint outlines of the original structures now obscured by volcanic deposits. This volcanic resurfacing underscores Mercury's complex geological history, revealing that it was once far more dynamic than its cratered appearance suggests. The planet's smooth plains and tectonic features also hint at processes that have shaped its surface long after its early volcanic period. Messenger provided a detailed map of these features, giving scientists a clearer understanding of the forces that have sculpted Mercury over billions of years. Unlike its terrestrial neighbors, Mercury possesses a magnetic field, albeit a weak one. Messenger's instruments detected this field and found that it is offset from the planet's center by about 20%. This unusual configuration suggests that Mercury's outer core remains at least partially liquid, generating the magnetic field through a dynamo effect similar to Earth's. However, Mercury's magnetic field is far weaker than Earth's, raising questions about why it has diminished over time. Understanding Mercury's magnetic field offers a window into the processes that sustain planetary dynamos and why they weaken or fail, as seen on Mars and Venus. Messenger's measurements also revealed how the solar wind interacts with Mercury's magnetic field, stripping away particles and contributing to the planet's tenuous exosphere, a thin layer of gases that includes elements such as sodium and helium. After 4 years orbiting Mercury and sending back unprecedented data, Messenger's mission came to a dramatic close in 2015. Running low on fuel, the spacecraft was deliberately guided to impact the planet's surface, becoming a permanent part of the world it studied so meticulously. During its final orbits, Messenger continued to transmit valuable data, providing high-resolution images and measurements of Mercury's surface features. The loss of Messenger marked the end of an era, but left a legacy of discovery that continues to shape our understanding of the solar system's smallest planet. Its findings have laid the groundwork for future missions, including the European Space Agency and JAXA's Bepi-Colombo, launched in 2018. This joint mission aims to build on Messenger's discoveries, with advanced instruments designed to explore Mercury's magnetic field, surface composition, and interior structure in even greater detail. Mercury may be the smallest planet in the solar system, but its importance in understanding planetary formation and evolution is immense. As the closest planet to the Sun, it offers a unique perspective on the effects of solar radiation and gravitational forces. Its dense core and unusual surface features challenge existing models of planet formation, while its magnetic field and water ice deposits provide clues to the processes that shape both terrestrial planets and distant icy worlds. Mercury's extremes, its searing heat, freezing cold, and volatile history make it a fascinating subject for exploration. It is a reminder of the diversity and complexity of the worlds within our solar system, each offering a piece of the puzzle that helps us understand our cosmic origins. The insights gained from studying Mercury not only deepen our knowledge of this enigmatic planet, but also inspire new questions about the forces that have shaped our celestial neighborhood. The story of Mercury is far from over. With Bepi-Colombo set to arrive in Mercury's orbit in 2025, a new chapter of exploration is about to begin. This mission promises to answer lingering questions about the planet's formation, geology, and magnetic field, while uncovering new mysteries that will push the boundaries of planetary science. As humanity continues to explore Mercury, we are reminded of the ingenuity and persistence required to unlock the secrets of the solar system. From Mariner 10's pioneering flybys to Messenger's groundbreaking discoveries, Mercury has been a proving ground for innovation and a source of inspiration for scientists and dreamers alike. In the vast expanse of the cosmos, this tiny, resilient world stands as a testament to the power of exploration and the enduring curiosity that drives us to reach for the stars. When Mariner 9 arrived at Mars in November 1971, it became the first spacecraft to orbit another planet. However, it was greeted by an unforeseen challenge, a global dust storm that engulfed the entire planet. Mars is known for its dust storms, but this one was unprecedented. For weeks, the planet's surface was completely obscured, leaving scientists with nothing but images of a red haze. Despite this initial setback, Mariner 9 patiently waited for the storm to subside, a testament to the resilience of early space missions. When the dust settled, the spacecraft unveiled a Mars that was far more intriguing than the barren world glimpsed by its predecessor. Mariner 9 revealed enormous volcanoes, vast canyons, and evidence of ancient riverbeds carved into the Martian surface. The spacecraft's cameras captured images of Olympus Mons, the largest volcano in the solar system, towering 21 kilometers high and spanning over 600 kilometers across. It also mapped Valles Marineris, a canyon system stretching nearly 4,000 kilometers, 10 times longer than Earth's Grand Canyon. Perhaps most tantalizing were signs of water erosion. Dry riverbeds and floodplains hinted that Mars may once have harbored liquid water on its surface, raising the possibility that the planet could have been habitable in the distant past. For scientists, this discovery transformed Mars from a desolate rock into a world with a dynamic history and potential for life. Mariner 9 laid the groundwork for future exploration. In 1976, NASA's Viking program became the first mission to successfully land on Mars and conduct experiments directly on its surface. Two identical spacecraft, Viking 1 and Viking 2, each consisted of an orbiter and a lander. The orbiters provided high-resolution images of the Martian surface, while the landers performed a series of biological experiments designed to detect signs of life. The Viking landers touched down in carefully selected locations. Viking 1 at Chrysoplanitia, a flat plain, and Viking 2 at Utopia Planitia, a region thought to have once contained water. Equipped with robotic arms, the landers scooped up soil samples and analyzed them for organic compounds. The experiments returned puzzling results. While chemical reactions suggested some activity in the soil, no conclusive evidence of microbial life was found. The findings sparked decades of debate among scientists and emphasized how challenging it is to interpret data from alien environments. Despite the inconclusive results, the Viking mission was a monumental success. It confirmed that Mars is a harsh environment, with a thin atmosphere composed mostly of carbon dioxide and surface temperatures averaging -60 degrees Celsius. It also revealed that the Martian soil is rich in iron, giving the planet its characteristic red color. These discoveries deepened humanity's fascination with Mars and set the stage for more advanced missions. After the Viking program, there was a 20-year gap before NASA returned to Mars. In 1997, the Mars Pathfinder mission ushered in a new era of exploration. Unlike Viking's stationary landers, Pathfinder included a small robotic rover named Sojourner, the first rover to traverse the surface of another planet. Sojourner was a marvel of engineering, a solar-powered rover roughly the size of a microwave oven, equipped with cameras and scientific instruments. Pathfinder landed in Ares Vallis, a region believed to have been shaped by ancient floods. Over 83 days, Sojourner explored the surrounding terrain, analyzing rocks and soil and transmitting images back to Earth. Its mobility allowed scientists to study a variety of features up close, providing valuable data about the planet's geology. The mission also demonstrated the feasibility of using rovers for planetary exploration, paving the way for future missions. Pathfinder's success reignited public interest in Mars and proved that relatively low-cost missions could achieve significant scientific breakthroughs. It marked the beginning of a new chapter in Mars exploration, one characterized by innovative technologies and a focus on mobility. With each mission, Mars has revealed itself as a complex and fascinating world. From the towering Olympus Mons to the ancient riverbeds carved by water, the Red Planet continues to challenge our understanding of planetary evolution. The data collected by Mariner 9, the Viking landers, and Mars Pathfinder laid the foundation for modern exploration, shaping the missions of today and tomorrow. Mars is no longer just a distant speck in the night sky. It is a destination within reach. As humanity prepares to send the first crewed missions to Mars, we stand on the shoulders of the pioneers who first dared to explore this enigmatic world. The journey to uncover Mars's secrets has only just begun, and the promise of discovery beckons us to continue. The end of opportunity marked the conclusion of an era defined by unprecedented longevity and scientific discovery on Mars. Yet, it was only the beginning of humanity's deeper exploration of the Red Planet. The successes of Opportunity and Spirit underscored the potential for advanced rovers to unlock Mars's secrets. These early robotic explorers transformed our understanding of Mars as a dynamic world with a rich geological history and signs of water, fueling aspirations for future missions. In 2008, NASA launched the Phoenix lander, targeting Mars's polar region for the first time. The mission aimed to study the frozen plains of the Northern Hemisphere, searching for water ice and clues about Mars's potential to support life. Equipped with a robotic arm, Phoenix excavated the icy soil, confirming the presence of water ice just below the surface. It was an incredible breakthrough, direct evidence of water on Mars, in a form accessible to future exploration. Phoenix also analyzed the chemical composition of the soil and found perchlorates, salts that could serve as a potential energy source for microbial life. These discoveries hinted that Mars's polar regions could be more habitable than previously thought. However, the harsh polar winter eventually ended Phoenix's mission, as dwindling sunlight rendered its solar panels useless. Despite its brief operation, Phoenix left a lasting legacy by showing that Mars's polar ice could play a crucial role in future exploration. Building on the success of past missions, NASA's Curiosity rover landed on Mars in 2012 as part of the Mars Science Laboratory mission. Unlike its predecessors, Curiosity was nuclear-powered, eliminating the reliance on solar energy and extending its operational lifespan. Its landing was a marvel of engineering, using a sky crane to gently lower the 1-ton rover into Gale Crater, a site chosen for its potential to reveal Mars's ancient environmental conditions. Curiosity's mission went beyond identifying water. It sought to determine whether Mars could have ever supported microbial life. Within its first year, Curiosity discovered a rock sample containing carbon, hydrogen, oxygen, and nitrogen, key elements for life. It also found evidence of an ancient lake that existed billions of years ago. These findings reinforced the idea that Mars was once a habitable world, with environments capable of supporting life. The rover's state-of-the-art instruments allowed it to analyze soil, rocks, and the atmosphere in unprecedented detail. Curiosity also detected methane in the Martian atmosphere, sparking debates about whether the gas was being produced by geological processes or microbial activity. This tantalizing discovery hinted that Mars might still harbor life in some form beneath its surface. The success of Curiosity paved the way for Perseverance, NASA's most advanced rover yet, which landed on Mars in 2021. Perseverance targeted Jezero Crater, believed to have once housed an ancient river delta. Its mission, to seek signs of past life and collect rock samples for eventual return to Earth. Equipped with cutting-edge tools, Perseverance is conducting experiments to determine Mars's potential for future human exploration. Its MOXIE instrument has successfully produced oxygen from the Martian atmosphere, a crucial step towards sustaining human presence on the planet. Perseverance also carried Ingenuity, a small helicopter that made history by achieving the first powered flight on another planet. Ingenuity's success demonstrated the potential for aerial exploration of Mars, offering new perspectives and access to previously unreachable areas. Mars has evolved from a distant curiosity into a focal point of scientific ambition and human imagination. The discoveries made by robotic missions have shown that the planet was once warm and wet, with the right conditions to support life. While no definitive evidence of life has yet been found, each mission brings us closer to answering the profound question: are we alone in the universe? The exploration of Mars also serves as a stepping stone for human exploration of the solar system. Plans for crewed missions to Mars are already underway, with nations and private companies envisioning a future where humans live and work on the Red Planet. From studying its geology and climate to unlocking the secrets of its ancient past, Mars remains a world of infinite possibilities. The journey to Mars has been a testament to humanity's ingenuity and determination. From Mariner 9's pioneering orbit to the incredible longevity of opportunity and the groundbreaking discoveries of Curiosity and Perseverance, these missions have laid the foundation for the next chapter in space exploration. Mars has become more than just a destination. It is a symbol of human curiosity and our relentless quest to explore the unknown. As we continue to study this enigmatic planet, we are not only uncovering its secrets, but also charting the course for humanity's future among the stars. The Parker Solar Probe represents humanity's boldest attempt to study the Sun up close. Armed with a heat shield capable of withstanding temperatures up to 1,370 degrees Celsius, it will plunge into regions never before explored. This groundbreaking mission seeks to unravel some of the Sun's deepest mysteries, including the nature of the solar wind and the mechanisms behind the Sun's million-degree corona, which paradoxically burns hotter than its surface. Understanding the Sun's behavior is critical, not only for comprehending its impact on Earth, but also for preparing future missions to the outer reaches of the solar system and beyond. The Parker Solar Probe's daring journey marks the closest a spacecraft has ever come to our star. It will perform multiple flybys of Venus to adjust its trajectory, a gravity assist technique honed by decades of interplanetary exploration. These maneuvers will allow the probe to spiral ever closer to the Sun, making observations that could redefine our understanding of solar physics. The data it collects will inform how solar storms form and how they interact with planets, potentially revolutionizing our ability to predict space weather events that can disrupt life on Earth. While Parker dives deep, the Solar Orbiter, a joint mission by ESA and NASA, launched in 2020, provides a broader perspective. The orbiter's mission includes capturing high-resolution images of the Sun's poles for the first time, offering a vantage point never seen before. The poles are critical to understanding the Sun's magnetic field, which drives its 11-year cycle of activity. Together, the Parker Solar Probe and the Solar Orbiter are creating a holistic picture of our star, answering fundamental questions about its workings and its influence on the solar system. Mars's history is intricately tied to the Sun's activity. Billions of years ago, when the Sun was younger and more active, its intense solar wind stripped away much of Mars's atmosphere, transforming the planet from a warm, wet world into the cold, arid desert we see today. Evidence from missions like NASA's MAVEN orbiter, Mars' atmosphere and volatile evolution, suggests that the Sun played a pivotal role in Mars's climatic evolution. MAVEN has measured the rate at which Mars loses its atmosphere to space, revealing the Sun's enduring impact on the planet's habitability. As humanity continues to probe Mars, the insights gained there also inform our broader understanding of planetary evolution. Mars serves as a natural laboratory, a smaller and simpler version of Earth, where scientists can study processes that shaped the terrestrial planets. Its geological record provides clues about the early solar system, including the interplay of planetary atmospheres, magnetic fields, and solar activity. The study of Mars has also inspired innovations that extend beyond planetary exploration. Technologies developed for Martian rovers, such as autonomous navigation and advanced life support systems, will be critical for future human exploration of the Moon, Mars, and even more distant worlds. These missions demonstrate that studying Mars is not just about understanding one planet. It's about preparing humanity for a future among the stars. Mars's transformation and the Sun's dynamics remind us that no planet exists in isolation. The solar system is an interconnected network where each planet's history influences the others. Earth has been fortunate to maintain its magnetic field and thick atmosphere, shielding it from the Sun's harsher effects. Without these protective layers, life on our planet might never have emerged. Comparing Earth to Mars, Venus, and Mercury offers a powerful tool for understanding what makes a planet habitable and what conditions foster or hinder life. The next frontier in solar and Martian exploration lies in further collaboration between humans and machines. As robotic missions like the Perseverance rover continue to unlock the secrets of Mars's past, they also lay the groundwork for human explorers. Meanwhile, missions to the Sun are providing the data needed to safeguard astronauts from radiation, as they venture farther from Earth's protective magnetic field. NASA's Artemis program aims to establish a sustainable human presence on the Moon by the end of the decade, with an eye toward using the Moon as a launch pad for Mars. Artemis will provide valuable experience in long-duration space missions and test technologies needed for deep space travel. The lessons learned from Artemis, combined with insights from Mars and solar missions, will shape humanity's path to becoming an interplanetary species. The Sun and Mars represent two sides of the same coin, the forces that shaped our solar system and the planets within it. While the Sun is the source of life-sustaining energy, it also poses challenges for exploration and habitability. Mars, as a neighbor, offers a glimpse into a world that could have been Earth-like, but fell victim to the Sun's destructive power. Together, these celestial bodies highlight the delicate balance required to sustain life. Humanity's quest to understand Mars and the Sun is a testament to our innate curiosity and resilience. From the early flybys of Mariner to the daring descent of Parker, each mission builds on the legacy of those before it, pushing the boundaries of what is possible. As we continue to explore, we not only uncover the secrets of our solar system, but also chart a course for the next great age of discovery. In doing so, we reaffirm the unyielding spirit of human exploration, an enduring drive to seek, learn, and ultimately thrive beyond the confines of Earth. Humanity's drive to explore is woven into our DNA, pushing us to seek answers to questions about our place in the universe. From the Moon to Mars, Venus, and beyond, our neighboring planets have been more than mere destinations. They are mirrors reflecting the history and potential future of Earth. Each mission, whether robotic or crude, builds a bridge toward a deeper understanding of these alien worlds and our own. The Parker Solar Probe exemplifies our relentless pursuit of knowledge. Designed to withstand extreme conditions, its heat shield ensures survival as it ventures closer to the Sun than any spacecraft before it. This mission isn't just about enduring heat. It's about answering fundamental questions. Why does the Sun's corona burn at millions of degrees, far hotter than its surface? What mechanisms drive solar winds that influence the entire solar system? The answers will illuminate the Sun's workings and improve our ability to predict solar storms, protecting Earth's infrastructure and preparing us for deep space exploration. As Parker dives into the Sun's mysteries, humanity moves closer to unlocking the secrets of our solar system's engine. This understanding is vital not only for planetary science, but also for safeguarding astronauts on future missions beyond Earth's magnetic shield. Mars, our closest planetary neighbor, has captivated scientists and dreamers alike. But transitioning from robotic exploration to human colonization presents unprecedented challenges. Unlike the Moon, which is just days away, Mars requires a 6-month journey, with communication delays of up to 20 minutes each way. A round-trip mission could last over 2 years, demanding technological and psychological resilience from its crew. The environmental conditions on Mars are harsh. With no magnetic field or ozone layer, radiation poses a constant threat. Surface temperatures can plummet to extremes, and the thin atmosphere, composed primarily of carbon dioxide, offers little protection or support for human life. Colonists would need to live underground or in heavily shielded habitats to mitigate these dangers. Beyond survival, sustainability is paramount. Crewed missions will depend on in-situ resource utilization, ISRU, the ability to extract water, oxygen, and fuel from Martian resources. Water ice buried beneath the surface could be transformed into drinking water, breathable air, and rocket fuel. Developing such technologies will not only enable Mars colonization, but also offer breakthroughs applicable to Earth. The prospect of colonizing Mars raises profound ethical questions. Mars, while barren to our knowledge, may harbor microbial life beneath its surface or in polar ice. Until we can definitively determine its sterility, we must tread carefully. Contaminating another planet with Earth-based life could erase any chance of understanding its true nature and history. Should we succeed in colonizing Mars, how do we balance human needs with planetary preservation? Is it our right to terraform a planet, potentially destroying whatever natural processes or organisms exist there? As we reach for the stars, we must remember that exploration comes with responsibility, a duty to respect and protect the worlds we encounter. The challenges of interplanetary exploration are daunting, but they also drive innovation. Technologies developed for space missions have already revolutionized life on Earth, from medical imaging to telecommunications. Addressing the hurdles of Mars colonization, radiation shielding, closed-loop life support, and efficient energy systems will likely yield solutions to pressing issues on Earth, such as renewable energy, sustainable agriculture, and climate resilience. Moreover, the pursuit of Mars fuels inspiration. As humanity unites to solve these challenges, we are reminded of our shared potential. The quest to explore Mars isn't just about reaching a distant world. It's about demonstrating what we can achieve when we collaborate, innovate, and dream big. Mars is more than a destination. It's a stepping stone for humanity's journey into the cosmos. By studying Mars, we uncover Earth's past and potential future, gaining insights into planetary evolution, climate change, and the delicate balance required to sustain life. Each mission to Mars prepares us for even greater adventures, to the moons of Jupiter and Saturn, to asteroids rich in resources, and perhaps one day to exoplanets orbiting distant stars. Exploration is at the heart of human progress. The discoveries made on Mars and the Sun don't just answer scientific questions. They inspire future generations to look up and wonder. As we push the boundaries of our knowledge, we also expand the boundaries of what's possible. The journey to Mars is inevitable. Whether through NASA's Artemis program, SpaceX's Starship, or international collaborations, humanity is poised to take the next giant leap. These missions will be fraught with challenges, but they will also be milestones in human history, charting a path toward a multi-planetary existence. Mars will not be the final frontier. The lessons learned there will propel us outward, to worlds we have yet to imagine. Each step into the unknown strengthens our understanding of the universe and our place within it. Exploration is not just about survival. It's about thriving, about creating a future where humanity reaches its fullest potential. As we prepare to leave bootprints on Mars, we are reminded that the drive to explore is intrinsic to who we are. The question isn't just if we can go, but what we will discover and who we will become when we do. In the vast expanse of the cosmos, Mars is just the beginning. Our journey has only just begun. Thank you for watching. Don't forget to like, subscribe, and share your thoughts in the comments below. Until next time, keep exploring.